Well, good day, everyone. It's a pleasure to welcome the committee members, our speakers, and our panelists today, other colleagues, and members of the public to this online open session of the National Academy's Committee on Attribution of Extreme Weather and Climate Events and Their Impacts. My name is Jim Hurl. I'm a professor of atmospheric science at Colorado State University, and I have the honor and the pleasure of serving as chair of this committee. In just a bit, I will ask the rest of the committee to very briefly introduce themselves. First, I'd like to emphasize our expectations for conduct in this meeting. In particular, the National Academies is always fully committed to fostering a professional, respectful, and cordial environment where all participants can participate fully. All forms of discrimination, harassment, and bullying are prohibited in any NASM activity, including this online information gathering session today. Just a bit about the study. The committee has been called together to examine current scientific understanding of attribution of extreme weather and climate events and their impacts to climate change, as well as consider user needs and opportunities to improve attribution science capabilities. As such, this study is an update, but also an expansion of the 2016 National Academy study on this same topic. The sponsors of the study are listed on the slide. Please go to the study website by either scanning the QR code on the screen, typing in the indicated URL, or simply Googling and allow your preferred search engine to direct you to the study website. About the study, I would like to remind everyone that this is an information gathering session. That is, the committee is in the process of assembling materials that it will examine and discuss while making its findings, conclusions, and recommendations. Therefore, I ask everyone here today, to be extremely mindful of the fact that the committee has made no conclusions and that it would be a mistake for anyone to leave here today thinking otherwise. Comments made by individuals, including members of the committee, should not be interpreted as positions of the committee or the academies. In addition, committee members typically ask probing questions in these information gathering sessions that may not be indicative of their personal views. I also wish to emphasize that today's meeting is the first of several upcoming opportunities for the committee to gather information as input to the report. For instance, the committee will be holding another online meeting on March 11th to gather information on process-based modeling approaches for attribution sciences, as well as a two-day workshop on impact attribution in Irvine, California, the 1st and 2nd of April. You can also find study updates, upcoming events, as well as provide feedback on this study by visiting the committee's website. Finally, I also want to emphasize that the committee will deliberate thoroughly before writing its draft report. Once the draft report is written, it must go through a rigorous review by experts who are anonymous to the committee, and the committee then must respond to this review with appropriate revisions that adequately satisfy the Academy's report review committee, as well as the Academy's president, before it is considered an official Academy's report. If you have questions about the study, please contact the study director, Stephanie Johnson. Now, if we could move to the statement of task, I'm going to just briefly highlight some aspects of the statement of task. The committee has been tasked with providing an updated assessment since the previous National Academy's report of current scientific and understanding of attribution of extreme weather and climate events, as well as their impacts, to discuss the value of attribution science and identify the utility of attribution for different applications. Can we pull up the statement of task, please? Assess current capabilities for the attribution of impacts, then very much related to today's session, examine methodologies of extreme event attribution, identify challenges, and provide guidance for best practice. Assess the maturity of both research and operational efforts to produce predictive probabilistic forecasts. Provide guidance about how to extend the application of attribution science to regions experiencing extreme events without well-established capacity. Provide guidance for methods to engage different stakeholders with the results of attribution science, and identify research priorities moving forward. So let's move to the committee roster. As I said, my name is Jim Hurl, and I have the pleasure of serving as chair of the committee. I would like the committee members to just briefly introduce themselves by stating their name and affiliation and turning on their camera for that moment in time. So I'll start with Hillary.
Hi, everyone. I'm Hillary Boudet. I'm a professor in the School of Public Policy at Oregon State University.
And we'll go down the list, James.
Hi everyone, I'm James Doan from the NSF National Center for Atmospheric Research. I'm a weather and climate scientist.
Nicole Jackson cannot make it today, so Joyce.
Hello everyone, my name is Joyce Kimutai. I'm an attribution scientist at the Imperial College London.
Can we go back to the committee roster, please? Al.
Morning, Al Lin, Professor of Law at the UC Davis School of Law.
Hi, I'm Jennifer Marlin. I'm a senior research scientist at the Yale School of the Environment and the executive director of the Yale Center for Geospatial Solutions.
Hello there, my name is Tim Palmer, and I'm a professor in the Atmospheric, Oceanic and Planetary Physics department at University of Oxford in the UK.
Hello, everyone. My name is Kevin Reed. I am a professor and associate provost at Stony Brook University and chief climate scientist at the New York Climate Exchange.
Hi, everyone. I'm Deepti Singh. I'm an associate professor in School of the Environment at Washington State University.
Tanisha, are you here?
Morning, colleagues. I'm Tanisha Stevenson. I'm a climate science professor at the University of the West Indies Mona campus in Jamaica.
And Dennis? Maybe Dennis isn't here. Danielle?
Hi, I'm Danielle Tuma. I'm a research assistant professor at the University of Texas at Austin.
Hello, everyone. My name is Grace Yan. I'm a professor in civil engineering of Missouri University of Science and Technology.
All right, thank you, everyone. Really appreciate those introductions. So let's move to the next slide. I'm just going to briefly introduce today's agenda. So today's session is going to include two panels of very brief flash talks, about 5 minutes each, and then a moderated question and answer discussion. First, starting with speakers discussing well-established methodologies used for extreme event attribution, followed by a session on emerging methodologies. After those two sessions, we'll move to a third moderated question and answer session with all the speakers that we have today on future directions for extreme event attribution. Before I turn it over to my colleague Kevin Reed to moderate the first panel discussion, I just want to issue a couple of very brief reminders. Again, the purpose of this meeting is for the committee to gather information from today's speakers on methods, approaches, and data sets used for extreme event attribution. All attendees in today's meeting are welcome to submit questions to the panel moderators for question and answer in the meeting. There will be both a link and a QR to Slido on the next slide, where you can also upvote others' questions that you're most interested in. When you log into Slido, please enter your name so the committee can keep track of who is asking the questions. We will need to prioritize, however, questions from the committee during this meeting to make effective use of the limited time and to prioritize the information gathering purposes of the meeting. If time allows, we may address additional attendee questions after the committee questions. This meeting is being recorded and will be available on the event page in the days following the meeting. So now I'm going to turn it over to one of our committee members, Professor Kevin Reed, who will be moderating our first panel today. Kevin?
Okay, thanks, Jim. So now we get to get into some of the topics of today's open session. So our first panel is focused on well-established methodologies used for extreme event attribution. Here, we use the term well-established to refer to methods that currently have more standard protocols and or are relatively prepared to operationalize. We will begin with a series of flash talks of 5 minutes each from our invited speakers listed here on the slide, and then we will move to a moderated panel Q&A discussion as Jim just outlined. Please, as a reminder, use the link here for Slido if you have questions as we go through the flash talks or if you're interested in upvoting others. So with that, our first speaker is Peter Stott, who is a science fellow in attribution at the UK Met Office and a professor in detection and attribution at the University of Exeter. So with that, I'll turn it over to Peter.
Well, thank you very much, and thank you for the invitation. I'm just waiting to see my first slide. So in order to introduce what we do, and I'm particularly going to focus on the Met Office and our interest in extreme event attribution and its application, I wanted to start with a statement of our purpose. We're the National Meteorological Service in the UK. We provide weather services and leading climate science, in particular to help everyone stay safe and thrive. And that really can divide into two parts. And I want to illustrate how we use event attribution to meet both the staying safe, i.e. early warning, and thriving in terms of providing information that can help people and stakeholders become more resilient to climate variability and change. So if we go to the next slide, my first illustration in terms of early warning and how we have applied well-established methodologies. So we could go to the next slide, please. In 2022, we had an extreme heat wave, and this was the first time the Met Office had issued a red weather warning for extreme heat. A red weather warning is the highest level of warning and was because we had a weather forecast from the Friday of that week in July for the beginning of the following week for extreme heat and for the first time to exceed 40 degrees Celsius in the UK. This was weather that we really wanted people to take note of. And our messaging was strongly supported by using event attribution, a well-established methodology that we had published a couple of years previously that looked at the odds of having 40 degrees Celsius in the UK using couple model simulations and a downscaling approach to work out what the odds were. And we could then use the basis of that study together with the latest observational information, and we put out information before the event had actually happened based on our attribution information. And this was valuable to us in our public communications because we could make the point that this was not something that people would be used to. We could make the point that this was related through a well-established peer-reviewed study to climate change, and therefore something that needed to be taken very seriously. If I go to the next slide, I want to come to my second illustration. And this was work that we did in collaboration with the World Weather Attribution Group. And this was the winter of 23-24 in the UK, when we had a whole succession of storms coming through, providing significant impacts in terms of flooding and strong winds. And this was something that we did also in collaboration with the Met Aaron, as well as the KNMI. So this was an example where National Meteorological Services worked together. And we did a study here in rather slower time. So in fact, we published this, we published this study in May, following the winter, and we did a rather careful analysis using the well-established protocols and methodologies that have been developed by scientists, including at the World Weather Attribution Group. And that allowed us to provide quantitative information, in particular about how heavy rainfall had changed in these storms. This was, to an extent, what you might call conditional attribution, based on how heavy rainfall had changed. And we were able to provide quantitative information based on peer-reviewed methodologies. If I now go through to the final slide, I want to draw some conclusions about what we have found is necessary for us in terms of the application of extreme event attribution. So if we could go to the next slide, please. I'm just waiting for that to come up. Thank you. The key considerations for us in terms of applying these methodologies for application are that it is very important that we understand the requirements and in fact the purpose of a service, which is the mode in fact we've moved to at the Met Office now, that we apply these methodologies in the form of a service, an attribution service. We ensure that key stakeholders are involved in study and dissemination. For example, in the storm example, the National Met Service is affected. So it is very important that we define and follow a predetermined protocol, including a process event for event definition. We employ scientifically robust methodologies based on peer-reviewed research. We incorporate appropriate quality assurance procedures into the methodology. It's important to be fully transparent in terms of publishing details of methods, etc., on the release of the results. And it is important also to attempt to deliver as clear user-targeted communication as possible. And a final point to make before I close is that in our experience, a whole range of timescales may be relevant, from days prior to the event to months or even years later. So there's a range of timescales on which it is appropriate to apply these event attribution methodologies. So I will stop there. Thank you.
Thank you, Peter. Our next flash talk is from Claire Barnes. Claire is a research associate in extreme weather and climate change at the Center for Environmental Policy at the Grantham Institute at Imperial College and works with the World Weather Attribution Group. Claire, I will turn it over to you for 5 minutes.
Great, thank you very much. I'm going to talk about World Weather Attribution's perspective on extreme event attribution, which actually will overlap a little bit with what Peter's just talked about. So if we can go to the next slide, please. So World Weather Attribution was established specifically to answer the question of how did climate change affect this extreme weather event while the media are still talking about the event and while the public is still aware of the event. That means that we typically try to get our whole analysis and report finalized and published within 1 to 2 weeks of the event occurring. So obviously that puts some pretty strong constraints on any methods that we use, which are outlined in the bottom corner here. Obviously the methods must be rapidly deployable. We have a global focus, so the methods have to be globally applicable. And because the studies aren't peer-reviewed before we publish the results, everything we do has to be really robust and really transparent. So all the methods that we use are peer-reviewed. And the results have to be easy to communicate and to understand. But we also want to provide as nuanced and comprehensive a picture as possible. So the key feature of World Weather Attribution's approach is to focus on the impacts of the event. And that affects everything from how we define the event right through to including a review of other non-weather factors that increase the vulnerability and exposure in the region and contributed to the impacts, which is a really important feature. We also always work with local experts throughout the whole process, from defining the weather event to communicating the results, to ensure that what we publish really does reflect the current state of the science. So if we can just move on to the next slide. So we know that this approach works. We know that we get a lot of good media pickup. We also know that this approach is really highly appreciated by stakeholders beyond the media. These are just a few examples of politicians that have referenced our work when talking about responding and adapting to extreme weather events and climate change. So if we can move on to the next slide, please. So to be able to produce our reports so quickly, we follow an established protocol, a fairly fixed protocol. We use statistical modeling of a class of events, including the event that caused the impacts. And this allows us to get a first order estimate of the effect of anthropogenic warming, if you like. Often the hardest part of this process is defining the event that led to the impacts. And it's vital, as I said, to do this with local experts who have a really thorough understanding of the meteorologically important processes and information on what actually happened in the area. And they'll help us to define an index that characterizes that weather event. So in our reports, we often use a simple linear regression of the index against the GMST. This is what you can see in the figures on the left. And this statistical model allows us to assess changes in both the likelihood or expected frequency and intensity of similar events in response to global warming, which is what you can see visualized in the figure on the right. When it's relevant, we will also include other covariates to reflect large-scale influences such as ENSO or the NAO or the IOD. So at the bottom here, we have an example of a study on flooding in the Horn of Africa, where we found a really strong influence from the IOD on rainfall in the region. And critically, we combine results from observations with results from climate models to understand the attributable signal. And that's what's shown in the middle in this synthesis plot with the red and blue bars. Of course, more complex statistical models could be used, spatiotemporal models, dynamical adjustment to account for changes in circulation patterns. The challenge then would be whether we can reproduce that more complex statistical model with the climate model output, and then how we combine those more complex results with results from the observations, although this is something that we are working on. So if we can just go to the last slide, please. So on the top left, I've just recapped those requirements for what we need to be able to do rapid attribution, which are really also the advantages of the statistical approach for this purpose, I think. Obviously, a limitation of the method is that it relies on the availability of a long time series of observations of the event, similar events, and climate models that can simulate similar events as well. But even where the data aren't available or where we aren't able to find an attributable signal, it's really important once we've decided to do a study to report that as the result and to discuss why that's the case. So I wouldn't say that's always a limitation in that sense. Obviously, the need to condense a 3D weather event into a univariate index really constrains the kind of events that we can evaluate. But these simpler models, again, they have the advantage that they're not only easier to interpret and communicate, they're also relatively easy to apply, which is really important for not only for rapid studies, but it makes them very accessible, which is very important for capacity building, especially outside the global north where computing power might be less available. And the final point I want to make is just that it's always really important to support and contextualize those results with other lines of evidence. So in our reports, we are increasingly combining these probabilistic results with results from other methods like analogs, which I know Davide will be talking about, to try to work around some of those limitations. So a key question is which of these other methods can add the most or the most useful information to complement the statistical approach?
Thank you, Claire. Next, we will move to our final flash talk, which will be given by Davide Ferranda. Really quick, Davide is a research director in the climate physics at the Climate and Environmental Science Laboratory at the French National Center for Scientific Research. Sorry, Davide, I will turn it over to you for your 5 minutes.
Thank you for having me. It's a pleasure to be here. So I will present ClimaMeter, that is a relatively young effort to perform rapid attribution of extreme events to climate change. And as Claire said, our perspective is more methodological. In fact, we use atmospheric circulation analogs. Next slide, please. So ClimaMeter is an observation-based rapid attribution framework, which means that we use reanalysis only, and we do not make use for the moment of climate models. And as the world weather attribution is a network of scientists all over the world from several institutions, which guarantee our independence from a specific office that can be attached to the analysis. And the idea is to have reports very, very fast, immediately after the events, in 24 to 48 hours after the events, with all the reports on Zenodo. And so they have a DOI and they are citable from other peer-reviewed studies. We are young, but we are quite active with 70 events in 15 months that have generated over 2,000 international press articles, as far as we could find in the news aggregator. You have on the right-hand side a map of the events that we've covered so far, with light blue that represent windstorm, dark blue that represent floods events, yellow heat waves, purple cold events, and a red one that is the Los Angeles fires, which I will focus later on. We can see also that in ClimaMeter changes are not red or blue in the sense that are not only in most of the case driven just by climate change or natural variability, but we have something in between, and we can detect when changes are due both to anthropogenic climate change and natural variability. And we also have a feature that is the event rarity that allow us to classify the events from a scale that goes from rare to very exceptional meteorological event that is the kind of events that we did not yet see in our data set. Can we go to the next slide, please? So where ClimaMeter is in this pathway to attribution. So attribution starts from the right-hand side here, from the impacts, and these impacts are caused by climatic hazard, but ClimaMeter goes to the level of the atmospheric circulation, causing the event. So it looks at the weather patterns in terms of cyclones and anticyclones that generate climatic hazard that cause impacts, and try to understand the differences between climate variability and greenhouse gases emissions in triggering these weather patterns. Therefore, we can cover at the same time multiple climate hazards, and we can add the statistical evidence that we will find from the data of changes between factual and counterfactual periods, the methodological reasons that cause the changes, and therefore this will strengthen our understanding of the changes that we can see. We can go to the next slide, please. So here it's a bit of a summary of the approach of the motivation. The idea is to use circulation analogs and look at analogs of the event in past and present period, and to make difference between present and past, and see how the methodology linked to a specific event has changed from the present to the past. And to realize only our reanalysis data. For the moment, we are using ERA 5 data completed by the GFS and DCMWF analysis forecast that we use to get the data up to the real time. And that's the reason why we can be fast and also have this physical interpretation of the attribution with minimal computational demand. That means that if we see changes that are consistent among different variables, we can link them back to the meteorology and support them with our understanding of the meteorology of the phenomena. So, of course, this methodology is best suited for events that are dominated by the atmospheric circulation and, in particular, at the mid-latitude. So we can cover events that have a strong signature in the pressure patterns, such as extratropical cyclones, but also tropical cyclones, heat waves, cold spells, and heavy precipitation extreme events at large synoptic scale. Of course, the limitation is that we lack a full process-based modeling and the models, and that we depend on the assumption that we can make core analysis data. Next, I will just show you very briefly what we see for the Los Angeles fires. That is one of the events that we have already covered. Next slide, please. So this is more just to show you the kind of figures we get when we do a ClimaMeter that has a first line where we have the 2 meters that then go to the statistics that I've shown you before, where we have the meter between natural variability and climate change, and we have the rarity of the event. A first line of figures that shows you the variables in terms of pressure, temperature, precipitation, and wind speed during the event, and then the changes present minus past. Here you can see that we have higher temperature, drier condition, and stronger winds that makes the LA fires more intense because of climate change, at least the risk of having the fire. And I conclude with the next slide by just showing you the QR code and the 2 references that support ClimaMeter study, and to remind you that there are also other studies that, as the world weather attribution, we can produce as peer-reviewed studies, and these go to increase the body of knowledge about attribution of extreme events to climate change. Thank you for your attention.
Hey, thank you. All right. Well, thank you all 3 speakers for those flash talks. I know it was a lot to cover in just 5 minutes, so we really appreciate that. And so now I welcome all of our panel 1 speakers back for a Q&A discussion here for about the next half hour. I just want to remind everyone that, as Jim said at the start of the session today, we are prioritizing committee member questions during today's session due to the time constraints and to prioritize the information gathering purpose of the meeting. However, all meeting participants are able, including committee members, are able to submit your questions via Slido, which was provided on the slides. And And so I will also be moderating and looking at those as we begin our session here. So I want to start with a question that actually was something that all of you have already hinted at during your talk, which is which gets at the fact that for some different types of events, certain methodologies for extreme event attribution seem to work better than others. And so I guess let's just start with a kind of high-level question. Why is it that why are some extreme event attribution methodologies more routinely used over others? Is it because of the specific event types, the applications, or the uses of the output, or modeling capabilities? And so this is kind of an overarching question that will probably drive a little bit of the conversation. So I don't know, I see all of the speakers are nodding a little bit, so they have some ideas. So maybe just not to go in the exact order that we already had our flash talks. But Claire, do you have any initial thoughts on the question? And then I'll turn it over to you, Peter.
Yeah, of course. So, I mean, as I said, everything that we do, well, weather attribution is kind of driven by trying to do things rapidly. So we need events that we can simplify down, I guess, into that univariate index or a very simple index in order to summarize, let's say, a maximum temperature over an area, maximum rainfall over an area. And that really does limit the kind of events that we can look at in terms of what we can just summarize in a unit. You know, there are some events that we just couldn't capture all of the nuance that we would need to in that kind of univariate index. Obviously, we're also then limited as to the duration of the event. So by kind of model availability, certain events that we're not going to be able to study because of the model resolution isn't sufficient to capture them at either small spatial scales or small temporal scales. I think that's probably one of the larger constraints that we run into after just being able to, can we even describe it in a kind of one-dimensional way? Are the climate models going to be able to capture it is really the next thing that would stop us, I think. And model observational availability, of course.
Yeah. Thanks, Claire. Peter.
Actually, I was going to pick up on the last thing that Claire got to there, actually, which is the model evaluation step. I think for me, the really crucial part of it is that evaluation, and that's a large part of the question you posed, Kevin, for me. You know, so for example, some of the illustrations I came up with were the 40-degree heat wave, for example, where our evaluation had told us that the method that we had available to us using based on the CMIP database, the couple model intercomparison database, we had good confidence that the models could represent that well enough to make that analysis and to release it. And then when the other example that I illustrated there was the UK storms, where we then used a variant of a different methodology. In effect, we used a different set of models, including actually the large ensemble of models at 60-kilometer resolution that we had available to us at the Met Office, the so-called HAGM-3A ensemble, which we have previously published, shows us that at 60 kilometers it represented features of the UK storms that were sufficient for us to do that particular analysis. But if, for example, we were looking at flash flooding in a city like Leeds, which is an example that we're currently researching, then for there we are looking at very high resolution models and using flood inundation models. So that would not currently be an event that we would be able to do this rapid attribution with. So a lot of it for me is about the model capability. Yeah,
thanks, Peter. And maybe before I turn it over to Davide to add, I guess kind of hearing from both you and Claire there that that to some extent, the methodologies, at least the models that are used as part of the methodology that you're both referring to, kind of requires existing. And you should correct me if I'm wrong, but I'm trying to summarize a little bit, existing research and a model evaluation to show, even outside of the context of extreme event attribution, that these models are suitable for looking at specific type of events. And because of that, especially if you're using models that are on the order of climate timescales as part of CMIP or those that are run routinely, that because of that, there are certain types, such as finer scale flooding events or mesoscale convective systems, these type of things that might be challenging these models, that those aren't necessarily well suited, in part because you're focused on, or in part because you're constrained by the models that you have. However, that there are then other extreme event attribution approaches that you can then apply in those cases that are still within tools within the tool belt, I guess, for kind of an analogy, that can then be used, but not as rapidly, at least at this point. Is that a fair kind of high level summary? Yeah. Okay.
I think so. Yeah. And I think therefore the research into model evaluation in particular is a very key one for me, and having those peer-reviewed papers available to you that says yes or no, this is currently the models, these particular suite of models are currently capable of a particular type of analysis is a key aspect of the research that underpins some of this application that we've been talking about.
Yeah, thank you. Davide, did you have anything to add?
Yes, perhaps that with the analogs we can solve partially this issue of not having like uniformly distributed or similar observable values that then we can unify on one single index, because we can look at a map of changes. But on the other hand, before applying the analogs framework, we have to prove the link between the extreme events and the circulation, and this link is not always the only thing that matter for the events. For example, we do not cover droughts because they are on a longer time scale, and because we know that there are other effects that come from example from the land, and we do not cover events that are on very small scale, because in that case we are not looking at synoptic signature of extreme events in the circulation, but we will need perhaps to find other observables that are more linked to the convection. So the analogs can provide a map of changes that can give you, in some case, a special distribution of changes, but on the other hand, you have to be sure that your events are really linked to the circulation before using them. So that requires additional research. And also the model evaluation part, it's very important, because we have not only to understand if the models can reproduce some statistics of some observable, but also the link with the circulation must be good in the model in order for us to implement the model in the analogs framework.
Yeah. Thanks. So I'm actually that's a good segue into the next question that comes from the committee. And you all three already touched on this a little bit in your response to the first question, but I kind of want to dive into it a little bit more, which is, what are some of the main limitations of the current, more routinely used approaches for extreme event attribution, and how can we overcome them? And so, I think, interpreting what all three of you just said, that one of the main limitations around the kind of more routinely used approaches is the resolution, the grid spacing of the underlying models that are routinely used for some of this analysis. And it's actually just not grid resolution. I think, Claire, you kind of alluded to this as well, that it's also a temporal thing, that some events are really high, maybe occur over a very short duration, and that might be the challenge, and it's not the resolution itself. So of course, it seems that the answer to this question, just is a higher resolution, but that comes, of course, with the lack of the ensembles that are needed for the type of statistical approaches that you've all alluded to in your work. And so let's dive into this a little bit more. What are some of the, outside of the resolution, what are kind of the main limitations to these approaches that you've all highlighted? Does anybody... Davide, want to start?
I mean, I think that there are other two things that I see as emerging. One is when we have events that are record shattering, that are not in the data set. So at the end, we have, from our point of view, we have no analogs. And in that case, it's very difficult to make any statement, or the level that, for example, is computed with the statistical approaches is so high that then there is no actually a return time that we can compute in a reliable way. And the other point is that there are many counterfactual words that are not just with and without CO2 emissions. Some times the impact of the event is determined by how we use the land or how we modify some urban areas. That's the case, for example, for Valencia, the Dana, where the impact was caused by how the urbanization has been done around the river that flows through Valencia. And this is very difficult for us to take into account. It could be reported in our reports, but we do not have really a model to deal with that unless digging into more specific studies that cannot be very rapid.
Yeah, Peter.
Yeah, I was just going to follow on with this thought about not just resolution, but we've mentioned ensemble size, Kevin, and that's something that we've thought quite a bit about in terms of, for example, our atmosphere-only model simulations and building up quite large ensembles, which means that we can sample extreme events reasonably well, and I think we're going to hear probably about ensemble boosting in the next session, perhaps. So, aware that itself is not necessarily going to capture extreme events, and we need to use statistical approaches. The other point I wanted to make was about structural model uncertainty. So, the looking at and this is something that's a common feature of the world weather attribution approach and the approaches we've done at the Met Office without the world weather attribution group, which is to look across model uncertainty across, for example, the CMIP ensembles, and look to see how robust attribution results are across those ensembles. And we do see, in some instances, quite a bit of uncertainty due to that structural model uncertainty, which is important to take that into account and synthesize as best we can across the model range.
Yeah, you're right. I think we'll get some into some of those aspects in the next panel as well, and we can come back to it maybe in the final panel with everyone. Claire, did you have anything to add or?
Sorry, failing to unmute myself. Yeah, I think I'm very much in agreement with what the others have said. I'm not sure that just adding spatial and temporal resolution is going to be enough to make the models better. I don't know how many studies there have been on looking at kind of just downscaling approaches in that sort of way and the effect of just adding resolution, but my impression is that it's more processes that we need to improve. Aerosol representation seems to be a really big one in the climate models, because obviously we have very specific constraints. We have to use an ensemble of opportunities, so we need to use what is readily available. I'm sure Peter at the Met Office has access to models that we either are not so aware of or don't have access to. So I think that's also a really important thing to consider, is just making higher resolution models, if they are then not accessible to people globally, is not really improving the situation globally, if you see what I mean. That's sort of 2 points that I've segued a little bit, sorry. So yeah, just improving the resolution is not the only thing that needs to be improved, I think, about climate models, but also making sure that everyone has access to these data sets so that anyone can do this, and not only modeling centers is also very important.
Yeah, I think that those points are really helpful, because I think it puts it into context that some of the limitations for the use of extreme event attribution, if I'm again trying to summarize a little bit what I'm hearing from the three of you, but that kind of comes out in your point, Claire, is that that it requires the continued development of our physics-based models that we use routinely into the weather and climate space, and that those process-based models are still really important for not only for climate simulations, but maybe for the event attribution type of approaches here, which brings up a point that nobody's kind of mentioned quite yet, but it comes up a little bit when, Peter, you were breaking down the different types or you mentioned structural uncertainty, and there's some other uncertainty in these simulations, such as the kind of boundary condition uncertainty. And so actually one of the questions that's come up in the Slido that I kind of want to reference now, it comes to the methods that are used for counterfactuals, right? So when you're actually doing the adjustment in some of these cases to what is your, pre-human-induced warming, how do you do that? I think all of the methods that you've all mentioned probably use slightly different approaches, and so we don't have to go into what those approaches are, because we have some other questions that I want to get at, but I kind of want to bring this up is if we are using different counterfactuals, is that an uncertainty that you account for in your practices already, or does anybody have any thoughts on that?
I mean, I don't know which order we want to go. I had a thought just on related to that, which is this is a really good point. This is an important point of important part of our process to construct those counterfactuals. One point I wanted to make about that was that, as you say, we could go into some detail about exactly how we can construct those, but it seems to me that one of the things that we check out is the robustness of the result to some of those choices, and part of that is seeing whether or not the changes that we're seeing between our counterfactual and our factual are consistent across different counterfactuals and into the future as well. So, we will often, we did this in the storm study for the UK, for example. We looked at the future predictions and what direction they were saying in terms of rainfall, which was a clear, robust result in that case, both in the future and in the past. And therefore, so different counterfactuals could be, for example, what happened historically versus the counterfactual would be constructed by, for example, changing CO2 in a couple model, etc. Or if we have an atmosphere-only model, changing sea surface temperatures as well as the atmospheric conditions. So there's an overarching point for me about checking the robustness of the both qualitatively and quantitatively about the nature of that signal that we are detecting when we look at those counterfactuals and what the difference is between the factual and the counterfactual.
Yeah, thanks for that, Peter. Well, maybe I think this is a topic that we should come back to, or maybe we'll come back to in the third panel, because I think this will also, we'll get a little bit of perception of this, I think, too, from the next panel, too. One question that I want to go back to that kind of came from the committee, which is, and we haven't quite discussed it much, but Davide, you brought it up a little bit in what happens when there aren't analogs for specific events, either in the models or in even in the observations. And so could we shift focus a little bit to talk about, are there current quality and availability of extreme event? Is the current quality and availability of extreme event data fit for purpose for extreme event attribution questions and applications? Of course, the observations are always changing, and over the historical record, right, there's been an improvement in a lot of the things that we talked about already: temporal resolution, spatial resolution, the inclusion of satellite data into some of the data sets and reanalyses. And so I'm curious if anybody wants to talk a little bit about the data and data availability and how that's used for extreme event attribution, and what are the challenges there for operationalizing some of this. Anybody want to weigh in on that, Davide?
Yeah, I mean, I can talk about the reanalysis data that we have used quite a little bit in this analogs framework. We've seen that we have to play the game that Peter was saying, that at the end we have to evaluate the changes that we see from the past and the present period also against the future. So even to use the reanalysis, what we have done, for example, in some PhD thesis that we had at CNRS, was to see how the changes that we can detect from the present observation and the past observation will evolve in the future, and therefore we will have to use climate models, the one that we trust to represent some extremes, to validate the changes that we already see as emerging signal from the past. So for me, the way to go is through model evaluation, and not all the models can be used as a bunch of things that we put in a washing machine and then we have some results. For each result, for each event, we will have to choose some specific models that is good at representing that events in that region, and then evaluate how changes evolve in time, and then go back and see if we see these already in our observations to counter-validate again the observation. So that's the procedure that I see, and the one that we are implementing with analogs. But of course, this is my 2 cents, and perhaps the others have different opinions.
No,
Claire?
I think I would agree with that. Sorry, Peter, if I just cut you off. But
No, go ahead, Claire. Go ahead.
Something similar. So yeah, I think there is no one size fits all with data. Unfortunately, we will try and use gridded data products, but we've carried out studies a couple of years ago in the DRC, Rwanda, there were terrible floods. We looked at 5 different gridded data products, and they all had the rain occurring at different times and in different places, none of which were actually over where it flooded and where people died. And so sometimes the gridded data products are really good, and sometimes they just aren't. And you have to evaluate it on a case-by-case basis, and it makes it there is no gold standard against which you can universally evaluate things. You know, you can try and get station data, but often in extreme events, the stations themselves are not running. So you can't always evaluate against that. And in many parts of the world, station data isn't freely available. So, I mean, our approach is always, we work with the locals and we say, this is the gridded data that we've got. Do you know of problems with ERA 5 in this region? Do you know of problems with chirps in this region? Whatever, you know. And we really do have to do that evaluation on a case-by-case basis. And sometimes we just have to say, we can't say anything. Now, for us, because we've committed to do a study, that would be our result. But obviously, depending on what the purpose is of your attribution study, that's not, I mean, it's not an ideal result. but highlighting that lack of data, I think, is also important on a kind of case-by-case basis as we're doing this, not to just say, oh, we can't do it, so we're not going to do it. Just to record that fact, I think, is important.
Peter, do you have a quick?
Yeah, just quickly. I mean, this just the basic point that we've all been making, the importance of the observational data, right, and the the value of, for example, like we have in the UK and in Ireland, we had the advantage of the 1 kilometer gridded data set. So the importance of building those data sets ideally across the world, big challenge, but often we can't do these attribution studies and a lot of other analyses simply because we do not have those scientifically robust and reliable data sets. So we need to build them and support them being built across the globe.
Yeah.
Just to finish, I mean, I would say that the effort that we put as a climate community in modeling the future is way bigger than the effort that we make in reconstructing the past, but and also to have a consistent past for all the world at the same time. And I think this is essential for attribution, is to have the past well reconstructed. So
yeah, that's a good point. So there's a couple questions. So there's a question from the committee, and then there's a few questions that are in the Slido that I think we have about 5 minutes for this question. And so I'm going to bring up a couple of them, and I'm hoping that each of you can touch on an aspect. And then I have kind of a final question I'd like to close with. So one question the committee has is kind of, how standardized are kind of the routinely used EEA, the extreme event methods discussed on this panel, and what were the challenges into standardize some of these approaches? And so you kind of mentioned some of these already, but I want to put it in the context of two kind of follow-up questions that I kind of are seeing also coming from the Slido. For example, you all mentioned the importance of model evaluation. So when there are events that are breaking records by a large margin, right? How does a standardized approach check that you're implementing, right, that the models are fit for purpose during the standardization phase, right? So when you get a case that's really outside the norm, right, how does the standardized operationalized approach handle that? So that's one aspect. And then another question that's kind of coming up, kind of related to this as well, is that I'm hoping folks can talk about, and I'll stop asking the questions in a minute. But when different methodologies, such as the WWA and the ClimaMeter, when they're looking at the same events, right, as folks look to see if they're giving the similar results. And so this is one of the advantages of standardization. So this is kind of an all-encompassing question, but I think it's putting us in a direction for each of you to maybe say something about a minute each on that broad topic, if you'd like. That'll be helpful for us. So just call Peter. Do you mind going first?
Okay, so a few points. So first off, instead of standardization, I would say the protocol, important point to make here, right? So the protocol meaning the set of steps that we need to follow to do these analyses, which will be standardized, and there might be slight tweaks differently across different groups, but they basically will contain the same basic elements in terms of a trigger, defining an event, doing the model evaluation, analysis, communication, etc. So that will be very standardized, and that's very important. In terms of the point about so I think the way I would address the question about if you've got something that's way outside the the norm or something. For me, this comes back to event definition in terms of using standardized approaches. It seems to me that if you are trying to so for example, trying to do an attribution around the probability that you have temperatures above a certain threshold. In the UK example, that might have been 40 degrees, but if we're going to push it way out to 50 degrees, then that's probably not something that we would be able to use our standard methodology in, or some analogy like that. So, because if it's way outside the extreme end and it's incredibly unprecedented, then I think we're in the realm of current research, and there's some very interesting research going on on this topic right now. So I think a lot of it in terms of standard approaches will come to careful event definition and careful evaluation of the statistical distributions of the metric that you are seeking to attribute. So those would be the points I would make.
Thanks, Peter. Claire, anything to add?
I would just add to that you would then just need to be really clear about what it is that you are communicating. Again, I'm thinking this very much from my point of view of communicating attribution for the public. We might not be able to put a realistic return period on an event like the 40-degree heat in the UK, but we can talk about how much hotter the hottest day of the year has got. So there is still something useful that we can say using these methods, even though, as Peter says, we are so far in the tail with some events that actually the kind of probabilistic side of it, you're just reduced to saying it's almost impossible that this could have happened without global warming. And I think from a communications point of view, for what we're doing, that is sufficient. And just to touch on what you asked about cases where ClimaMeter and World Weather Attribution have studied the same event, I don't think it's ever happened that we've come up with opposing answers, fortunately. But actually, having spoken to our comms guys about this, we do often have cases where we'll look at the same event, and journalists do seem to be able to deal with that and with understanding that there are two different numbers. And we saw this also with the Los Angeles wildfires. So many different groups put out, there was a group in LA, the Met Office said something, you guys said something, Davide, we said something, but actually the journalists were able to process that. And I think a lot of people now do have enough understanding of climate change and of attribution science to be able to say, okay, well, maybe they're not coming up with the exact same numbers, but actually they're saying this about this aspect, these people are saying this about this aspect, and those complement each other or are slightly different for whatever reason. So I don't see that as a problem. It's a communications question.
Yeah. Okay, thanks. And so we are running up on the time, so I'm going to have to move us forward. But I wanted to maybe add back to the introduction at the beginning from Jim, right, that the idea around communication, I think, is something that we'll be discussing in our workshop in April, and that's part of the statement of task of this committee. So it's really good to see that, and we could probably have some discussion in the third panel. So I am going to take the liberty to ask one more question with 10-minute responses, or 10-second responses, sorry, really quick, which is, if you could say what is one critical advance in like 10 words that would be needed for your approach to improve either its capabilities, extension to other events, rapidness, what would it be? Really, like, quick fire here. So Davide, do you mind going first?
I think we need a model that simulate well the relationship between the events and the internal variability of the climate system. We have this relationship at all the time scale is not well simulated, and I think this comes from the problem at the interface, sea, land, atmosphere, and the process representation, as has been said before. So we have to improve that and the availability of high resolution reanalysis data for the past.
Yeah. Peter, do you have a quick response?
So for me, so my proposal would be combining large ensembles with high res, potentially using machine learning. I think that's a really exciting avenue at the moment, and I think if we got these large ensemble high res data sets, I think that will advance things considerably.
Thanks, Peter. Claire, final words on this?
Yeah, I mean, one of the things that World Weather Attribution is very keen to do is to, as I said in the slides, increase capacity outside of the global north and get a bit more sort of local attribution and kind of training more people in these methods, making them more accessible, making the data more accessible. And the other thing that would be really good is to be able to do more impact attribution and link those hazards more directly to the impacts that we're seeing and quantify those V&E aspects, although that is a whole nother kettle of worms.
Well, I want to take this as an opportunity to thank the committee. Would like to thank all of you for the effort, for your flash talks, for this discussion. And of course, we'll be coming back to some of these topics later in today's session. But with that, I would now like to turn it over to committee member Danielle, who will be moderating our second panel. So thank you all.
Hi, thank you, everyone. That was a great panel discussion. I learned a lot, and I'm excited to hear more from our second panel. So for our second panel, we're going to be talking to people who use more emerging methodologies for extreme event attribution. So these are methods that are maybe not used in an operational setting or for rapid attribution, but are really exciting in terms of how they can be used to do extreme event attribution. So like panel one, we'll begin with a series of flash talks from our invited experts, and then we will move to a moderated panel, a Q&A discussion. So to kick us off, we're going to start with Dr. Kate Marvel, who is an associate research scientist at Columbia University and at NASA's Goddard Institute for Space Studies, or GISS. So Kate, if you want to go ahead and start us off in this panel, we're excited to hear from you.
Sure. Do you want me to share my screen or?
No, someone will share your screen and you can just let them know when you're ready to advance your slides.
Great. Okay, so I assume everybody can hear me. Awesome.
Yep, I can hear you.
All right, so I just kind of want to talk to kick this off in very, very broad generalized brushstrokes about the kind of new attribution world that we find ourselves in right now. Next slide, please. I don't think it's going to escape anybody's notice here. I think everybody knows this, that recently we've seen a real explosion in available computing power, but we've also seen real advancements in machine learning algorithms, methods, and sampling methods, which have really enabled the development of new approaches to statistical analysis in general and event attribution in particular. Next slide, please. So nobody has ever defined machine learning to me in a way that I find clear and understandable. And I don't think there is a definition of machine learning. But the way that I think about machine learning is basically you are asking your data to do a lot of work for you. And this requires very little knowledge, perhaps, of the underlying structure of why the data are doing the things that they're doing. You can use weak or uninformative priors. You don't necessarily need to know much going in about what your parameters are doing, how they behave. But there's a big assumption inherent in all machine learning methods, which is that training data are like the test data. And so machine learning really excels in situations where we've got a lot of training data that are more or less interchangeable with test data, or we can capture the difference between the training data and the test data in some sort of understandable model. And we don't necessarily need those full posterior estimates, or we can be satisfied with just bootstrapping them. Next slide, please. And machine learning excels in many different cases, but it's particularly good for classification. So we can ask, is this particular event categorically different from others? Is it an extreme event? And when you're looking at a univariate time series, that is an incredibly obvious question, right? But when you're looking across a really large spatial domain with a lot of grid cells, if you're looking across multivariate data, that can be a little bit more of a complicated question. And so there's machine learning methods which excel for outlier detection and really high dimensional data sets. Machine learning also excels at prediction. So given the observed or predicted values of all of these different variables in all of these different locations, will there be an extreme event? It is really good at sifting through really, really big data to kind of tell you what's going on. Next slide, please. Now, by contrast, I think of Bayesian inference as asking your model to do a lot of work for you. And so when you're doing Bayesian inference, it requires a really clearly specified underlying generative model for what's going on. It also lets you put priors on those model parameters, which can allow you to incorporate your existing knowledge, right? Like we all know physics, we all know that there's only particular values that physical parameters can take, and we can incorporate our prior knowledge even on top of that. And so Bayesian inference is really good in situations where maybe we have very sparse training data, but we want to infer the full posteriors on the parameters. Next slide, please. And there are a lot of really clear use cases for Bayesian methods in event attribution. We had a recent paper out in AGU Advances where we're looking at a fully Bayesian method for inferring the forced response and internal variability in a GCM-free context where we're just looking at the emergence of signals from paleoclimate data. It also excels for things like inversion or reconstruction. So given the known physical relationships, what underlying, probably unobserved or latent drivers contributed most to an extreme climate event? Next slide, please. Now, Bayesian statistics is often criticized for its inherent subjectivity, but I would argue that it requires you to make explicit assumptions that otherwise exist but are implicit. Next slide, please. And the meat of every analysis is in the construction of this likelihood here. What is the probability of observing the data given putative values of particular parameters? Next slide, please. And this can be really important in attribution analysis because the requirement that we specify this model means that, for example, we can look at counterfactuals. We can look at aerosols versus greenhouse gases versus internal variability versus natural forcings. So, for example, the way that we traditionally do this, and I'm sorry I came in late, I didn't hear the discussion for the last panel. But, for example, we can impose a linear regression model here. Next slide. Or we can assume that what we see is purely due to our best understanding of internal variability. Next slide, please. And what I just really want to reinforce, and I'm sure other folks are going to talk about this, is that every attribution statement is implicitly a model evaluation statement. How well does the model fit the observed data? So in some cases, when we're doing Bayesian inference, we have an understanding of what that model is because we have clearly specified it. In other machine learning cases, we don't necessarily know or care what that underlying model is, but we still need to do attribution as model comparison. So Bayesian methods allow us to essentially apply Occam's razor, where we're penalized for more parameters unless we have really good prior knowledge of what those parameters are, or they're really useful in generating the data. Next slide, please.
Okay, I just want to remind you that you're over time, so if you can wrap up.
Okay, and basically every attribution statement requires unavoidable choices about different models. Next slide. And this is my final slide, just sort of summarizing where machine learning is useful and where Bayesian inference is useful. Thank you.
Thank you so much, Kate. That was really interesting for me. So next we will have Nicholas Leach talking about their method, his methods. Nicholas is a postdoctoral researcher at the University of Oxford and is also a climate scientist at ClimateX. So Nick, when you're ready, go ahead and start your presentation.
Great. Can you hear me okay? I'll take that as a yes. Thanks very much for the opportunity for me to speak here. I just want to say that this is some work that's been mostly a collaboration between research at the University of Oxford and the European Centre for Medium Range Weather Forecasting, and in particular, Sharon Ermis, Miles Allen, Antje Weisheimer, and Tim Palmer. And it kind of builds off ideas that were first implemented by Pandora Hope and Lin Zhu at the Bureau of Meteorology in Australia. If we can move to the next slide, please. So basically the approach that I'm going to talk about, which we refer to as forecast-based attribution, but at BOM they call it MICAS, I think. And so it's motivated by the idea that we should use the models that have been explicitly designed and assessed on their ability to simulate both the physics and the extreme weather itself in order to understand how it's responding to climate change. So we're asking, how can we use weather forecasting models rather than climate models, but use them to answer kind of climate questions? And so one way of effectively doing that would be to have very large, as Peter talked about in the last session, to have very large ensembles of high resolution, kind of effectively weather forecast model output, but massive ensembles comparable to what we have for climate models at the moment. But that is beyond what is kind of, well, at the moment, technologically possible. And so we're talking about a kind of an alternative way to use weather forecast models to kind of get at similar questions. And so I'm going to start by trying to answer the question of what weather types is this approach useful for? And if essentially what we'd say is that it's suitable for any kind of event that your weather forecast model that you're using is able to predict. So you've got a pretty strong test on, is my model able to predict the event? And if it's not, then there's presumably something wrong in the underlying physics in the model and in its ability to simulate that process. And so you can't get to events that aren't kind of a subgrid scale in a weather forecast model. And so if I move to the kind of 3 bullet points. So one motivation behind this is trying to get at the dynamical response. So there's a real challenge there in terms of kind of climate model uncertainty in the dynamical response to climate change and how reliable climate models actually are. And when you use a weather forecast model, you can kind of tell from historical predictions how good that weather forecast model will be at simulating kind of crucial dynamical features and teleconnections. Another thing that I'm particularly interested in is using this approach to synthesize between kind of the so-called storyline and probabilistic framework. So by using very short lead time weather forecast, you can really kind of get at an answer that's similar to what the storyline approach typically gets at. And when you back off to kind of seasonal, potentially even decadal timescales in terms of your forecast, then you're trying to answer that kind of probabilistic unconditional attribution statement. And finally, a kind of practical reason for why we're doing this is because a lot of weather forecast models are already used in impact modeling pipelines. And so there's a much lower bar in terms of getting at impact attribution by starting from a model that's already built into an impact modeling pipeline than having to create one from scratch. And if we move to the next slide, I'm going to get into the details of the method. So what we're aiming with this method is to produce ensemble weather forecasts of what the weather would have looked like in either a past climate or a future climate. So what we've done, we've taken an operational weather forecast model. So in our case, it's been the IFS from the European Centre, perturb the initial ocean state in a way that is hydrostatically balanced, so you don't get kind of changes to the densities in the ocean, so you don't get spurious mixing as soon as you initialize the model. And we also changed the CO2 boundary conditions. And so the specific counterfactual that we're getting at is, what if both the ocean and CO2 concentration kind of instantaneously shifted to their pre-industrial or to a pre-industrial or future state at the start of the forecast? We then reinitialize the forecast and examine the downstream effects on the extreme weather event of interest. And so this kind of forecast framework, which you could implement on both a medium range but back to a seasonal, potentially decadal timescale, allows you to analyze different drivers that occur at different scales. And so this figure is from a study of Storm Eunice led by Chironomis, and this shows kind of these Eunice-like storms at a lead time of 4 days prior to the event in kind of past, present, and future climates. And now if we could move to the last slide. Kind of getting at this slide is effectively the limitations of the approach at the moment and what we're doing to try and account for them. And so the big limitation we have at the moment is that we allow the atmosphere to adjust freely. And so we're working to try and understand whether we can estimate a state-specific perturbation that we could introduce to the atmosphere to try and make it more consistent with what would the initial atmospheric state have looked like in a past climate or a future climate. We're also looking at how we can best synthesize across timescales. So rather than considering medium range up to seasonal as kind of separate attribution statements, is there a way we combine these potentially in a kind of, well, as Kate was talking about, a Bayesian framework to try and better come up with one kind of one result for an event rather than having multiple different ones that might be potentially be even conflicting. And the final focus, which is already mentioned, is to try and introduce aerosols because they're clearly very important for extreme weather events, and they're a kind of a pretty big gap at the moment in terms of how they're assessed. And with that, I would like to thank the committee for the opportunity to speak today. Thanks.
Thank you, Nick. So our next speaker is Laurent Terray, who's a senior research scientist at the European Centre for Research and Advanced Training in Scientific Computation, or SURFAX for short. Thank you, Laurent, for being here, and I look forward to hearing from you.
Thank you for having me today. So I'm going to talk about dynamical adjustments. It's just a simple approach to quantify the contribution of different drivers to an extreme event. So there are 3 very well-known events, and you can find the details in the studies below. Can you please go to the next slide? So dynamical adjustment is actually based on constructed analogs. So this belongs to the type of conditional approach, and there can be used to answer 3 types of questions. First, what were the relevant causal factors that led to an extreme event? Second question, how might climate change and or internal variability can contribute to those causal factors? And third, last type of questions, the what if question, for example, impact of the same event in a warmer or colder world. So the main step of the method is actually to estimate the mean contribution of the circulation. Like you can use any type of variable, atmospheric pressure, geopotential, stream function, different combination of this variable to the extreme event. So basically you partition the event on a variable X, can be temperature, precipitation, or something else in a dynamical part and a residual part. And as, of course, you are interested in changes, the effect of circulation, the X sub den is actually often estimated in the counterfactual world. Next slide, please. So this is an example for the June 2021 North America heat wave. On the left, you have this is based on ERA 5 data. In color, you have the temperature, the maximum temperature, and the geopotential at 500 millibar. In contours, you have the observed from ERA 5. On the left, you have the dynamical contribution, and you can see that, of course, due to the method itself, the construction of the circulation is perfect. And then you have the residual, and as you have estimated the dynamic component in the counterfactual world, the residual part includes the force component. Can you go to the next slide, please? So the different steps, the additional steps of the method is first to estimate the force contribution for the 2 components, the dynamical component and the residual. And then, of course, arises the question of how to define the counterfactual. It can be used by detrending methods, parametric and non-parametric, or constructing periods. For example, these 2 periods, if you are using ERA 5 reanalysis. Another step that is also very interesting is to try to understand the contribution of internal variability drivers. And to do that, you have to actually perform additional dynamical adjustments with analogs drawn from periods with contrasted surface conditions. It can be SST, it could be CI, it could be soil moisture, snow cover, etc., etc. For example, in the case of June 2021, we were able to show that the internal residual was actually mostly related to soil moisture deficit in North America. And now the third type of questions, the impact of the June 2021 omega block in a warmer climate. So in order to do that, of course, you have to use model. Here in this case, the CSM2 large ensemble. Can you go to the next slide, please? So you have at the top, you have the effect in the current climate. So 1 degree C warmer than pre-industrial. And then the 3 plots on the second row are showing you the change of the dynamical component at 1 degree, 2 degree, 3 degrees additional to present. And then you can see the effect on the heat wave. And basically, you were able to show that the dynamical component scales with a factor of 2 compared to the global warming level. Next slide, please. So just to summarize the strengths and the weaknesses of the approach. So the strength is conditional on the exact synaptic circulation, and that differs from the class of event approach. It uses standard analog methods. It's based on observations or reanalysis, no model runs needed, unless you want to, of course, look at the future. Can be implied in quasi real time. It provides uncertainty range thanks to some bootstrap methods. And also, very importantly, can be directly compared with other model-based methods. For example, nudge model runs, as in Verlier et al. Or Van Garderen et al., and also with the approach that Nicolas just presented. Caveats and issues. There's a sensitivity to the counterfactual definition, but of course can be estimated. There's a sensitivity to a spatial and time domains, as with any methods. So that can be documented as well, but it's important to keep in mind. You only assess changes in intensity and cannot do changes in occurrence frequency of the event. It's also a conservative estimate of the atmospheric circulation contribution, can have nonlinear relationships between circulation and other variables such as humidity that are not necessarily covered by the method. And then the current data sets are not always fit for purpose for this type of analysis. There are homogeneity problems in reanalysis, resolution problems, physical parameterization. And I just want to mention that there are some high-resolution data sets that are being either they already exist, like the Serra reanalysis, 5 kilometers over Europe, and there's a project ongoing with a 1.3 kilometer reanalysis over Western Europe done by Météo France that could be very useful for the last 60 years. So thank you.
Thank you so much, Laurent. Our next speaker is Sebastian Sippel. He's a junior professor for climate attribution at the Leipzig Institute for Meteorology. Go ahead, Sebastian. Thank you for being here.
Hello, everyone. Thanks for the invitation. Can you hear me well?
Yes, we can hear you.
Okay, great. Then next slide, please. So what I'm going to do today, I wanted to present 3 challenges in empirical statistical methods for extreme event attribution. And so I'm not really presenting kind of emerging method, but rather the results of a benchmarking exercise of conventional methods. So the first challenge I will present is about the statistics of very rare events. The second challenge is about aerosol representation in statistical extreme event attribution methods. And the third challenge is about the trends in dynamic versus thermodynamics. Next slide, please. So for the first challenge, and this came up already, we have seen a couple of events where that have been kind of widely exceeding any kind of statistical expectations. So for example, the heat wave in Western North America, where if you had kind of believed or trusted a statistical model that was based on the data prior to the event, then the actual event was far, far outside of any kind of statistical possibility. And so we've been asking in a series of papers, why is that the case? And next slide, please. So what I'm referring here is the very conventional statistical model for extreme event attribution on observation. So we're looking at a statistical model that fits a general extreme value distribution using global mean surface temperature as a covariate. And we're fitting this generalized extreme value distribution to annual maximum temperature data, so block maxima, over 70-year periods. And we're doing this in a large ensemble to each ensemble member separately in order to test how well the method actually performs on very rare events. Next slide, please. And this was a PhD study by Shoa Eseda. And what we found out was that we basically using this kind of benchmarking of the CSM2 large ensemble and then only applying the statistical model to any one ensemble member separately for the 100 members available, what we were seeing is that if we kind of impose a 100-year return level event, which we know exactly because we have the CSM2 large ensemble, so we have 100 members to kind of estimate kind of more or less the true 100-year return level, then we're seeing if we, with that many ensemble members here, so this is what you see in the top panel here, with these ordered ensemble members, many ensemble members are kind of the statistical models based on these individual ensemble members are underestimating the estimated 100-year return level by a little bit. So this doesn't seem to be so severe, but in the lower panel, you see that if this is translated to a return period, there's actually a sizable fraction where even a 100-year return level would be estimated as a kind of infinite return period event. And the reason of this is that the sample size is so small that it's really hard to estimate return periods very accurately when the sample size is so small. So basically the conclusion from the study is that the GEV parameter estimation can be biased in practical situations, partly because it's a kind of a finite sample exercise that we're doing here with only 70 years, but that kind of roughly reflects the observational data sets. And next slide, please. So meaning that, and this has come up already, but I just wanted to highlight this here again, that we really need careful statistics when we're talking about kind of doing extreme event attribution on small sample sizes, in particular when we're trying to estimate return periods for very rare events. We have kind of used this benchmarking for this conventional GEV-based method, but I would suggest that this actually holds for other statistical attribution methods as well, if we look at very, very rare events. Next slide, please. I'm coming to the second challenge. So this is about aerosols versus greenhouse gases in statistically extreme event attribution. So we are kind of still looking at the conventional model where we parameterize climate change as the change in global mean surface temperature. And now we're going to look at how aerosols are kind of coming into play there if they are not kind of adequately parameterized. So of course, aerosols have been, and this is what you see on the left slide, aerosols have been changing a lot. So in particular, Europe and North America has seen a very strong negative aerosol forcing in the 70s and 80s, and both Europe and North America are recovering from this very strong negative aerosol forcing. And this is kind of a regional effect that is not really incorporated into this global mean surface temperature covariate. So if we fit our kind of conventional statistical model with GMST as a covariate onto a time series such as Midwest US, which you see on the right-hand side, then this is again kind of exemplified in the CSM2 large ensemble. And you see the CSM2 large ensemble mean in black here. And the lines that we get from the statistical model are kind of these blue and orange and red lines here. And what we're seeing is that if we do not kind of explicitly parameterize the aerosol change and only parameterize the GMST change, then it becomes very obvious if we benchmark the method in the large ensemble that in the 1970s and 1980s, we are basically underestimating the exceedances of very rare extreme events, and we are kind of slightly overestimating them now as the aerosols are decreasing. So if we would compare basically based on this conventional method that's parameterizing on GMST change, if we would compare the present day period to, say, a reference period in the 60s or 70s or 80s in a region like Europe or the US, we would actually underestimate the true changes just because we had basically underestimated the exceedances in the 70s and 80s. So we basically suggest in this study in preparation that it would be very good to actually also develop method or incorporate kind of aerosol change in especially regional extreme event attribution studies. Next slide, please. Now I'm coming to my third study, and that's about dynamical versus thermodynamical trends in heat extreme. So I very much agree with and very much support the studies that by Laurent Terret and others that are trying to basically to disentangle dynamical versus thermodynamical trends. And we've done that in a study as well, where we looked at basically trends in dynamics and thermodynamics over Western Europe and over North America, which you see on the left side here. And what we found out is that actually in Western Europe, we see a trend that is very much driven by, to a large extent, driven by atmospheric circulation, whereas in the Midwest US, this trend driven by atmospheric circulation is actually decreasing. So in a sense, Europe and North America are behaving kind of in an opposite way in terms of kind of circulation trends, whereas the thermodynamic trends are relatively consistent between both regions. And this is, of course, very difficult and currently not fully accounted for in statistically extreme event attribution frameworks. And there are methods, of course, as Laurent Terret presented, that are emerging, that are kind of trying to disentangle circulation-driven trends and thermodynamic trends. However, the question that kind of emerges from there is how much the circulation-driven trends that we are observing, how much they are actually reflecting internal variability trends or circulation trends. And that is actually, I think, a very important challenge that we need to be able to answer in the long run. Next slide, please. So basically, I'm coming up and kind of the three challenges that I wanted to present for statistical methods for extreme event attribution studies is that with the statistics of very rare or even record-shattering events, we have to be very careful in evaluating probabilities because the sample size is usually very short, very small. Secondly, I do think that it is very important to incorporate aerosols, especially when we're talking about regional extreme event attribution studies. And certainly, this dynamical and thermodynamical disentanglement is very important, but then we need to also be able to say how much the circulation-induced trends may be driven by internal variability or force changes. And that's what I wanted to say. So thank you very much for the invitation.
Thank you so much, Sebastian. That was really informative. Thank you all to our panel 2 speakers. So now we'll bring all the speakers back for a Q&A discussion, just like we did in panel 1. And I will be moderating that Q&A. So as in panel 1, I'll be asking questions that the committee has prepared for this panel, and I'll also be taking questions from the Slido. So if anyone watching wants to ask some questions, you can put those in the Slido. So yeah, that was definitely a lot of information in a short period of time. But I think one thing that came up for me was there was a lot of discussion about data sets and what we need to be able to, what you guys need to be able to what you need to be able to for your approaches. And so I was wondering if you what you think of the current quality and availability of extreme event data that are out there for the certain events that you've studied or certain regions that you've looked at, and if they are fit for purpose. So one thing that came up for me when Kate was talking was the machine learning methods and how you really rely on a lot of data to be able to use for prediction or classification. And also that came up for me when Laurent was talking about what we can include to kind of account for variability, whether it's soil moisture or land surface conditions and whatnot. So does anyone want to take a stab at that question?
Sure. I can. Sorry, go ahead, Kate.
No, you first, please.
Okay. Well, for example, in terms of observed data, a lot needs to be done. For example, for precipitation. I mean, I remember a paper from my colleague Margot Badr about extreme precipitation, and you look at different data sets, whether they are, from satellite, in situ, or mixed, and they give very different answers for many parts of the world, not just in Africa or South America or the South Hemisphere, but also even in Europe. So that's one thing. And then, of course, as soon as you go in, you dive into the past, then things get even worse. So that's suddenly a very big challenge. And if you look at the number of in-situ data for precipitation, it goes down for the last 20 years now. So this is a critical point. Now, this being said, for some extreme events, and that's, again, some work from my colleague Margot Badr, you can even wonder whether sometimes a very high-resolution model, forecast model, can actually do a better job than observations. If you're in the mountain regions and you have radar-based precipitation, you have valleys separated by mountains, and the fact that you get different answers between the forecast models at kilometer scale resolution and the radar observations, it's not clear that the observations are right, actually. So in some very complex terrain, even getting the right observation is very challenging.
Yeah, I'll agree with that. And then going kind of in the other direction in time, obviously, when we talk about extreme events, it matters who we talk to, right? It matters whether we are making the case that these are truly unprecedented, and to what extent that matters from sort of an adaptation or legal or whatever standpoint. But if we want to understand the degree to which the events we're seeing are unprecedented, we do need data that extends farther backward in time, right? Because otherwise we're just going to say this is unprecedented in the 3 weeks we have this data set, which is not as helpful. And I think, there's a problem with that, right? Because paleoclimate proxies don't have a lot of high temporal resolution. We don't have very good observations before the satellite era. And as Laurent pointed out, we don't have perfect observations even in the satellite era. And I think that is a great use case for machine learning, but machine learning guided by humans. Because fundamentally, like, we don't want machines to learn, we want to learn. And I think maybe taking advantage of wildly disparate data sources, everything from paleoclimate proxies to in situ observations, to satellite observations, to even high resolution models, and finding ways to stitch all of those together so that they make sense and they capture all of the uncertainty inherent in having multiple data sets, I think is a really useful and interesting area to focus on.
Go ahead, Sebastian.
Okay. Yeah, I just want to say this was very nicely said, and I agree with both. So what Laurent said, that it depends a lot on the variable, and I guess later on there will be a session on impact attribution, and I'm also in my group working a little bit with carbon impact. So even not so much far away from the climate, it's a kind of ecosystem impacts of the climate, and even there the databases are very, very scarce, and so I do think that it depends on the variable, and also what has the statement that was made by Davide Faranda in the previous session resonated a lot with me, where he said that the number of people who are actually developing data sets is actually much, much smaller than the number of people that are kind of trying to model the future climate. Of course, we have to do both, but there is a lot of value for attribution science in actually basically reconstructing old data sets, and also what Kate said, I couldn't agree more that that machine learning is really a big opportunity for, bringing together many different data sets, especially in the past.
Nick, do you, with your method, it seemed like if the weather forecast model can get the forecast right, can predict an event, then you trust that model. But like, where does data come into play here in terms of historic data? How is that considered in your methods?
Yeah, so I was going to say it might seem that we're kind of a bit more kind of detached from the data set perspective than some of the other like purely kind of say reanalysis based products. But I mean, forecasts, they're dependent on their initial conditions, and so in the parts of the world where the initial conditions aren't as good, the models aren't as good, and so we're going to be able to naturally going to be able to make less reliable attribution statements using the methods using the forecast based method than we would otherwise be able to. I mean, one example of that would be Hurricane Otis, which was a complete forecast bust from the numerical models, and so for that one we wouldn't sort of even try to make any sort of statement using the model because it's clearly enabled to simulate the physics, and that could be improved by having would probably be improved by having better kind of coverage of observations used to initialize these models. The other kind of big challenge with our method is that we still need to be able to estimate like a delta, a perturbation to apply to the initial ocean state. And a really big challenge in the kind of the way that we currently do that is on how big the uncertainties are, not just in the sea surface. They are big, but they're way bigger as you go further down. And so the ocean subsurface is completely different depending on what data sets you use. And so that's a big, definitely a big challenge to the approach at the moment, and that uncertainty is something that we've not yet quantified, but yeah, would be good to.
Yeah, that's what I was thinking, that you would need the good historic data to kind of understand, how to initialize your models, especially for thinking about counterfactuals. So one follow-up question, maybe Kate would be the most appropriate for this, but maybe you can all answer if you've come across this in your methods, is how do you deal with different uncertainties around different data sets? So for example, how do you deal with, paleo data being maybe a little more uncertain than satellite or in situ observations, or kind of different, scales, whether it's temporal resolution or spatial resolution. So how do you kind of think about that when you're including it in your different approaches?
Sure. I mean, I'd love to hear how other folks deal with this. I would say that I'm really drawn to hierarchical modeling because I'm lazy and disorganized. And when you do hierarchical modeling, that keeps track of the uncertainties for you in building the model. And so I think that is my preferred method of handling uncertainties that enter from different data sets, from mismatch between timescales, from having data gaps. I think there's a lot of methods out there to basically say everything's a hierarchy, and you can truncate your hierarchy wherever you want. And you need to truncate your hierarchy somewhere in order to make your analysis tractable. But that for me provides a really flexible, useful framework to think about these things.
Thanks, Kate. Yeah, that's really interesting. That's a good way to keep track of your uncertainties. Does anyone else have any thoughts about this? Something they've come across in their own methods?
If I might to chip in, I mean, what I've presented today was largely about kind of a benchmarking exercise in a CSM2 large ensemble, but maybe, of course, kind of many people are doing these kinds of benchmarking exercise and uncertainty testing exercises of their method in large ensemble, and I think that the large climate model ensembles are really, really highly valued by the community. However, what exists, of course, in addition, and I know people are aware, but maybe it's worth mentioning, is that kind of many observations-based data sets also produce kind of large ensembles now by basically sampling the uncertainties of the observations. Like, for example, for Europe, the kind of standard data set is called the EOBS data set, and it has a number of kind of uncertainty ensembles, and also the Climate Research Unit data sets. They have kind of very comprehensive model, like uncertainty models for uncertainties in the observations, and there are people who have spent like the whole career on kind of trying to develop these uncertainty models, and I know people are aware and they kind of sometimes used, but they are not so often used. So maybe it could be something for the future to kind of build in these very comprehensive uncertainty estimates that sometimes exist for observation data that's a little bit more for event attribution.
Two things, if I can add. One thing, yes, it's a very good point. For example, of course, even if you use dynamical adjustment or any analogous method with reanalysis, you just have a very short sample. You just have like 70 years or even less, depending on where you put your counterfactual. But of course, you can always use models to actually try to estimate what sensitivity you have to this short period. For example, that's what I've done in this GL paper about the North American heat wave. I've used CSM2, which actually is quite reasonable in this region in terms of circulation and in terms of length between circulation and temperature. And then I was able actually to estimate the influence of internal variability on the dynamical component. Which actually was not negligible. It was plus or minus 1.5 degrees C for the dynamical component. So that's one way where you can combine model and observations. Of course, if you talk about precipitation data, then they're so different in terms of extremes that, and not only extremes, but just a PDF of them, that you would get probably very different answers. And of course, people debate endlessly about, what is the best, and of course, there is no answer to that. So the only option is actually to use as many as possible, and then to try to give a range of uncertainty, confidence interval in your results. So it's hard to see. It's hard to do something different. And of course, then you have this problem of your regions when you have just no data or the very poor quality data. So then, as many others have said, then the only answer is, oh, sorry, we cannot do the study. We just don't have the data to do it. So.
Yeah, if I can just very quickly jump in at how that kind of applies to the forecast-based approach. I think being a kind of numerical model-based approach, it's more challenging to kind of fully assess the uncertainties, because you would basically have to do the experiment. You'd have to add in the uncertainties into the data sets that are going into the approach. I think one particularly kind of, I don't know, interesting one is in the structural uncertainty that was talked about earlier. At the moment, we've just done this in one forecast model, and it would be really interesting to see how different the results between two forecast models are, because I suspect that they might be more consistent than you might see kind of from like a climate model perspective, because they're trying to they're more constrained, but I don't know that, and that's something that is really important to try and understand.
Yeah, that's also something that we definitely need to consider, the structural uncertainty, and we will have another information gathering session about modeling and how that's advanced in recent years to kind of support extreme event attribution. Thank you all for those answers. And so maybe shifting gears a little bit, and I just got informed that we have 4 minutes left for this panel discussion, and I don't want to take the 10-minute break away from anyone. So maybe let's go to maybe a quick question, and then we'll tie off with a last question. So I was wondering, for your method specifically, which types of extreme events kind of are more suited for your methods, and which ones have posed issues. And we talked about the data issue. So if we don't have good data for a certain event, but maybe reasons other than data availability, in terms of which events work best for your methods. And anyone can take it away. I'll pick on Sebastian.
Yeah, maybe just to refer back to this benchmarking exercise that we did, kind of the first challenge I presented, where we showed that the small sample size is really a big kind of statistical challenge to overcome. And what we saw at the beginning was that heat waves should be quite easy, because we thought that this is kind of typically the best understood event, the easiest to attribute, and so on. So we kind of expected that this GV algorithm, even with small sample sizes, works quite well for heat waves, but maybe doesn't work so well for precipitation and so on, where we have like all these other challenges. However, this wasn't the case, and actually this what we saw was that specifically on the heat wave case, the GV algorithm had kind of more problems than with precipitation events, and the reason was that the shape parameter, so that the shape of the GV distribution is kind of more difficult to estimate for heat waves than for precipitation. So this is not saying that precipitation is easier, precipitation extremes not easier to attribute than heat waves, but this particular uncertainty that I was referring to, the statistical estimation uncertainty, there we saw that even for heat waves, it can be quite tricky.
In the case of analogs, of course, as the VD has pointed out, I mean, when the links between the large scale atmospheric circulation and the impact on temperature precipitation are large, then of course these methods are very well suited to do that. Of course, even if the large scale is small, you still have a residual, and you can still try to interpret, I mean, to try to understand what are the different contributions to residual using different techniques. So, but of course, then the dynamical adjustment is really well suited to when you have a large scale circulation that is a dominant driver of the event.
If I can jump in, I mean, there's kind of the simple answer that I gave, which is that if your forecast model is unable to capture it, if it's like a subgrid scale process, then you shouldn't try and attribute it. And then there's this slight kind of more complicated answer, which is we haven't demonstrated, but I think would be really interesting, is that people are like, we have built kind of post-processing models and like machine learning type models that can predict these potentially more subgrid at scale. I mean, I've seen an example of a hail model that you put in ensemble forecast data, and it it's a kind of a generalized additive logistic regression type model that then says, well, this is the probability of hail. And so there is potential there for being able to start to attribute these kind of events that the forecast model themselves can't get at. But maybe if we have these statistical techniques to kind of put on the back end, we might be able to start doing it with our approach.
Yeah, sorry about the balloons. I don't know where they're coming from. I think it just got very excited about Nick's answer. I started working on drought attribution because that is the thing that is most clearly preserved in paleoclimate proxies. And the reason I started looking at that is I got a little bit freaked out by the fact that CMIP models do not appear to be able to capture the recent SSTs that we've been experiencing, both kind of over the AMIP period and notably in the past 2 years. And so I think there is utility for trying to do some of these methods in a GCM-free environment as kind of a check. Because I think Michael Weiner said at a meeting like 10 years ago, detection attribution is the most powerful model evaluation tool that we have. I think there are ways to move beyond just looking at PDSI or soil moisture or other kind of long-term drought indicators, because a lot of the paleoclimate stuff, especially over the last millennium, is biological, and we can see impacts of large-scale disturbances in that. And so I think there's an exciting new frontier in trying to look at extreme events vis-a-vis the ecosystem.
Yeah, that was really that's a really good that's a really nice way to go. Yeah, I feel like there's a lot of other data outside of climate that we can use to look further into the past and see what things were like back then. So I will wrap it up now. I won't ask my last question. We can get to that maybe in the third panel. But I really want to thank all the speakers for this discussion and their flash talks. We're now going to take a brief 10-minute break. And at 1 p.m., 1 p.m. Eastern time, we'll be back, and we'll have a third panel where all the speakers from both panel 1 and panel 2 will come back and for one final panel. And this will be moderated by Deepti Singh, who's one of the committee members. Thank you all, and see you in a few minutes.
I think we're still getting the webcast back up, so but there will be a countdown.
Nope, we're live. You can go.
Recording in progress.
Okay, should we get started then?
Yes, go ahead and start, Deputy.
Okay. Well, thank you to all the panelists for both panel 1 and panel 2 for continuing to stay. I know for some of you it's quite late in the evening. We really appreciate the opportunity to hear from all of you. So just a quick recap. In the first panel, we heard from some of the speakers that are working on some of these rapid attribution approaches where the methodologies that are pretty well established are being used for providing attribution within 24 to 48 hours or like within a short period of the events happening. And then in panel 2, we heard about some emerging approaches using different types of data sets and different methodologies that to some extent address some of the limitations in the more well-established approaches. So we greatly appreciated hearing both those perspectives. And so this is a time for more of a discussion on the future of extreme event attribution. And we'd love to hear from your perspectives on a few different topics. So one of them is the topic of standardization of methods, approaches, and data sets that could advance extreme event attribution. The second topic we're going to talk about a little bit is on communication of the results of our attribution studies, as well as kind of what we see as a future of attribution science. Yeah, so and just a reminder to everybody that's listening online, please provide your questions on Slido, and I'll try to keep track of those as well. But as you all are thinking about your questions, I thought I'll start with a couple. So the first question I had is around what kind of protocols or approaches or frameworks do we need to perhaps get at the standardization of extreme event attribution approaches. And this can include things like methodologies or data sets that as a community we think would be important to standardize. Is that possible? And what kind of events and landscapes could those be used for? I'll give everybody the opportunity to answer that question, but maybe we can start with panelists from the first panel, as they're already sort of working towards some of this. So would anyone like to jump in? Or maybe I could ask Peter to provide some initial thoughts.
Yes, I think you were asking about protocols. I think a clear protocol is really important. So a set of steps to follow through. And I think as different teams have developed protocols, I think there have been very similar elements to them. The reason why there might be some certain differences is due to the stakeholders, the users of the service, and that may be slightly different. And that's very important to understand what the use is. And there are a variety of different users, including the media, including citizens, including governments, including legal people, for example. You could think of a number of different users. I would say that the set of steps that you need to follow are probably rather similar, but there might be some slight differences and nuances. But it's really important to have those steps really laid out. But I would say, and I think Claire and David are nodding there, so disagree if this is not the case, but I think there's some very commonalities with that, and I think we've got a pretty clear idea now of what those steps are. Going from a trigger mechanism to the how you define your event, to the model evaluation step, through into the communication step.
Davide, would you like to share any additional thoughts?
Yes, I think I go in the same direction as Peter, but I think that the standardization to have just one global framework for everything is not possible, but we can definitely continue to make protocols and improve our protocols, both in terms of methodology, but like, for example, in ClimaMeter, we also have a protocol for writing the reports. and avoid our own personal judgment that goes through the attribution studies. So I think that we can improve the protocols, but each of us is specialized in something different. For ClimaMeter is the meteorological aspects of the weather extreme events that then turns into impacts for the population. And I think we will continue to protocolize this better. And I think that we both need international networks of independent scientists like the WWA or ClimaMeter, as well as national agencies that perform attribution studies, and these have different purpose, and I think they all deserve to exist alongside with peer-reviewed studies that are something that we cannot, of course, forget when we do attribution.
Yeah, just to kind of build on what Peter and Davide have said, I think having a protocol for your method is very important. I would caution against trying to over-standardize. I think Davide touched on that a little bit, because you do need different, yeah, you just need a slightly different approach depending on what you're doing. There is no one size fits all. And that would be the case, I think, with data sets. It would be great to have one data set that we could hold up as the gold standard, but if we can't rely on it to be the best in any part of the world, and I don't think that is likely to ever exist. Maybe it could, I don't know. There is a slight danger of over-standardizing, and then people will automate things that maybe should use a little bit more critical thinking. So I fully agree that some degree of here are the steps you need to follow is really important, but yeah, I think it's important not to be too prescriptive, because we've been doing studies at World Weather. Actually, we've done like 90 studies, and we still find new things that we need to tweak each time and things that we need to take into consideration. So I think flexibility is really important. One thing that I might think might be useful to standardize, and it's something we've been talking about, is how we communicate the results of attribution. Obviously, the IPCC has one set of kind of standardized language. I'm not suggesting that we adopt that, but so that we all interpret. Davide mentioned their protocol involves a report writing step to take your personal interpretation of the result out of things. And I think that something like that, to sort of how can we interpret a result like this, might be something that would be useful to talk about. I'll stop now, sorry.
I think if I can just add something, I agree, diversity is very important, but what's also very important is to understand why there's a diversity of results. And that's currently, I think it's partly missing in among the different methods. And of course, I mean, I remember one paper by my colleagues Aurélien Ribes and Julien Cattiot suggesting a way to define the spatial and time extent of the event by maximizing the probability ratio, for example, and that one way that you can at least reduce the, the fact that you have different ingredients to the method. So I think it's I'm not sure it's just a communication point, as Claire suggested during the previous panel. I think there's a little bit more to that. So I think it's something that we should still keep discussing and exchanging about.
Sorry, I didn't mean to say we should only standardize communication. That was not what I was meaning, but just I think that would be a useful area to look at. And just on to kind of address what you say about that optimization approach to event definition, that's not necessarily what we would want to do at World Weather Attribution, because we want to look at where the impacts happened, and for that we would speak to the locals who know, where did the rainfall that maybe flooded downstream, and there's a different area that you want to look at. So again, there are definitely lots of approaches that we can take to this, and this is why I think it's really important to consider multiple ways of doing things and not necessarily to try and come up with the way of doing things.
I agree, but communicating these subtleties to the general public is a real challenge. I'm not sure that the citizen lander is really understanding what is different between the WWA approach of defining the event and some other methods. So there's clearly a challenge there, I think.
Yeah, so thanks for the perspective. Oh, sorry, go ahead. You can finish your thought, please.
No, I'm finished. Yeah.
Okay. Yeah, thank you for that discussion, because I think it gets to some of the questions that were asked in the Slido forum as well, about how there are some uncertainties between different approaches, and perhaps there's an opportunity for comparison when there are findings. Perhaps there's an opportunity for some sort of comparison in the attribution findings from different groups, and that might be possible for some types of events, and perhaps more challenging for others. So maybe if some of the other panelists for the second panel can also touch on that, like what types of events is standardization possible for, and in your work, what do you find as like being as events that are more challenging to do that for? If it can either be events or regions where attribution is a particular challenge. So I'll open it. Maybe I'll start with Nicholas.
Yeah, thanks very much. So I guess kind of going back to touch a bit on the last question, we've been working on trying to do a study in which we compare several different methods that I know that some people in this panel are involved with. And it's a challenge. It's a real challenge, because at the moment, everyone kind of has very fair but very slightly different methodological choices. Like something as simple as how do you define what the pre-industrial climate is not very much not consistent across approaches. And some approaches that's by necessity, because that's how far back the data sets go, and others it's kind of trying to be consistent with maybe the Paris Agreement and things like that. So that's a big challenge. I think one kind of, I don't know, suggestion that I have that is probably not for communication but more for the science community is, as we do these comparisons, I think something that would be really helpful, although again this might just be a me thing, is understanding the extent to which your approach is conditioned. Because kind of we have these, like, we set up these like storyline approaches and then probabilistic approaches as two ends of a spectrum, but for different events, say the WWA statistical approach is not necessarily going to be conditioned to the same extent for another approach, because you by choosing your event definition, you might be picking out the same events that an analog approach is doing, but you just don't necessarily know. So I think for comparing the methods, it'd be really useful to have a kind of standard way, which I actually think the analog approach is kind of a nice framework to build it around, to understand to what extent is your approach conditioning on the dynamics, so that we can compare them in a more kind of, I don't know, consistent way. So we know if something is very conditioned versus very not. But that's just one suggestion that I have on this point.
Sebastian, go ahead.
One thought that came to my mind, I mean, it's not really standardization maybe, but there is of course also trend attribution and kind of a lot of studies on fingerprinting, even of extreme events. And I've been kind of thinking a little bit sometimes. I know that people from the attribution field, they often say, well, these are kind of two sides of the same coin and so on. And they are in some way, but still, I feel like sometimes results from fingerprinting studies also, potentially there could be like a little bit of a feedback effect that extreme event attribution studies could use those could refer to or use those kind of results from fingerprinting studies a little bit more to contextualize or frame extreme event attribution studies. I mean, I'm sure this is happening, but I mean, it's just something where I thought that maybe there could be kind of an interesting, a good positive interaction between kind of results that we have from fingerprinting or trend attribution studies and for extreme event attribution studies. So for example, in dynamical adjustment, just as an example, of course, like this disentangling between kind of dynamical contributions to an event and thermodynamical contributions to an event, this is really, really useful in itself. But at the same time, there have been many studies coming out in recent years that showed that kind of circulation-induced trends in Europe are very strong. But so far, I think it's kind of still out in the community to judge if those trends are really driven by kind of forced circulation changes or whether they are kind of internal variability. And so in the end, I guess the interpretation of extreme event attribution studies really hinges on kind of our understanding also of the long-term trends. So I think there could be potentially it could be quite useful to kind of to make a bit more the links between extreme events and the underlying trends and different drivers.
I guess, I agree a lot with Nick. I think, I've got opinions about uncertainty and standardization, both on kind of a scientific side and on the communication side. So on the scientific side, I think we have to be really careful not to conflate structural uncertainty and parametric uncertainty. A lot of times people sort of look at the possible distributions of a particular parameter and say, all right, well, now I have taken into account all of the uncertainty, and I'm going to report this with a misplaced and sort of overconfident attribution statement. And of course, structural uncertainty is not just parametric uncertainty, it is also model uncertainty, right? Because your parameters are contingent, exactly like Nick said, they're conditioned on the model, right? So for example, if you are trying to compare two models, one in which internal variability is stationary and one in which internal variability is coupled to the forcing, right? So it changes as the forced response increases. Those are two different models, right? And one is going to have a parameter that is not present in another model. Now, obviously, we're all using a whole bunch of different approaches. We're using analog approaches, which are conditioned on kind of, the analogs being, there being some commonality between analogs in the past climate and analogs in the future climate. And my point is that all of those are different models, right? And we have ways to handle different models, right? There's averaging processes, there's selection processes, there's weighting processes. But I think it could be really helpful to think about moving beyond just parametric uncertainty to a standardized way of taking into account different model uncertainties. On the communication side, I actually kind of want to disagree a little bit with Laurent in how difficult it is to convey uncertainty to the public. I think it is difficult to get the time and space to talk about uncertainty, but there are ways to talk about uncertainties. There are ways to even talk about really sort of in the weeds scientific uncertainties in ways that engage different audiences, make people curious, make people feel like they're being trusted with information, and sometimes even make people entertained, depending on what group you're talking to. So I think, I guess I do agree that it is very difficult to talk about uncertainty, but I don't think that we should cede ground on that. I don't think that we should preemptively surrender and say, well, this is just too difficult, the general public won't understand it. I think there are ways to try to do that.
Well, I agree, but that means we understand the uncertainties, because if you don't understand what are the sources of uncertainty, then you would have a very difficult time to speak about. So my point is just that currently I think we don't necessarily clearly have a very precise assessment of what the methods gave different results in some cases, not in all cases. And I got the point that maybe it doesn't matter if the change of probability is something that differs by 20%, or that the confidence interval in one case is plus or minus 200%, or plus or minus 50%, or whatever. I don't know. I'm still wondering why this is not a problem, but so that was just my point. So another point I would like to comment about is, for some event, and the June 2021 is a very interesting event. There's been so many papers about that event. It's still not fully understood. It's an event. It's a multi-compound event. There are many drivers, factors. So I still have to convince myself that to encapsulate that in one univariate index does tell us something about this exact event and the way that this event is going to be more probable in the future. So it's a subtle point, but I think it's a very critical point, and it can be applied to not all events. There are some events that are much easier. This one, it's just the aggregation of many different processes that most GCMs are not able to resolve correctly. Atmospheric rivers, intraseasonal teleconnections, soil moisture deficit, etc., etc., etc. So philosophically, I still have a problem to say, okay, I have one univariate temperature of a region there, and then I look at models and I look at the exceedance of temperature in models, GCMs, 150 kilometer resolution global, and then I'm still able to say something about this event. So I'm curious to see what other thinks about that.
Well,
Oh, sorry.
Oh, sorry. Yeah, thanks for sharing your thoughts about this. Clearly, it's a challenging problem, and I think there are several sources of uncertainty that we need to deal with, both in our scientific work, but also in communication of the attribution findings. And so maybe I have perhaps one more question on this topic, and then I'd like to move towards the couple of the other topics since we have relatively limited time. But on this topic, maybe you can each take a minute or so to answer the question of what do we think is actually needed to truly assess different methods in a comparative way. This could include either sort of some standardization of how we define events, which I kind of agree with Claire that it's challenging to do, especially because they occur on different, like there can be events on different timescales, which are relevant to different impacts. But yeah, maybe you could each share some thoughts on what do you think is needed for such an assessment. One of the things that, as a committee, we had a question about was how do we define counterfactuals in a systematic way that enables that standardization or comparison or intercomparison of methodologies. Yeah, maybe if you all could keep your answers relatively short, since we're almost at 10:20, that would be great. And maybe I'll start here we'll go in the reverse order. Kate, do you want to share some thoughts on that?
I was actually hoping to hear from some of the other people first, but I think we will never be able to define, like to have a singular definition for what is an extreme event, right? Like we're just never going to be able to do that. We're never going to be even able to have a definition for a particular subcategory of extreme event. Like I remember when we were writing up the National Climate Assessment, and there are 120 different definitions of drought in the published literature. But I think there is space to work with other communities, to work with, for example, the legal community, and say, hey, it doesn't necessarily matter what scientists think drought is or what scientists think a heat wave is. What does this court think a heat wave is? What does the judicial system think a heat wave is? And even if that may not be our optimal definition, go from there. In regard to counterfactuals, I also think it's important to talk about future counterfactuals as well. I don't know how much you're thinking of this, but I think a particular use of event attribution is how do we know whether or if climate policies and reductions in emissions are having impacts, and talk about the difficulty of counterfactuals over the past. Counterfactuals over the future are a whole different can of worms.
Thanks. Yeah, some of the speakers in the first panel had touched on that a little bit, but yeah, thanks for making that point. Okay. Anyone else want to share some thoughts on that topic?
Can I go ahead? So just following on from Kate, that I was yeah, it's a really good point from points from Kate there. In terms of sort of comparing the models and their reliability, if you like, with estimating these metrics. So first choose your metric. But when you've done that, I mean, for example, at the moment we're conducting a study where we're comparing a number of different ways of calculating these extreme temperatures in the UK. So, to go into a little bit of jargon, the unseen method, the statistical method based on observations, the attribution approach that we've using the HADGEM3 SST forced ensembles, etc. And we've spent quite a bit of time comparing these. So having chosen a metric, and you could obviously do it for different ones, but one that we've shown in the past has a particular resonance, with in the UK. and then comparing the different methods and seeing how well they compare, and trying to delve into the differences. And what we are trying to do there, actually, and this was touched on earlier, is the rather hard problem of not just calculating the change, the relative change in the probability of 40 degrees in this case, but in terms of the absolute probabilities. And we feel in current research that we're currently writing up that we actually have a handle on that absolute number, because we've got a bunch of different methods that are giving us numbers, which actually is giving us a slight update in previous outputs, which raises an interesting question for consideration, which is, as science moves on, these results may change, and back to the communication, we need to be clear about how we are going to communicate that. The results that we may produce now, which I would argue we should only widely disseminate in terms of the public output, we should have some confidence in them, but nevertheless, new science could mean that those results could change, and that's something I think to bear in mind as we go forward.
Thanks, Peter. Sebastian, go ahead.
Yeah, I mean, just two quick points. On the comparison of methods, I agree with Peter and others that, I mean, kind of comparing different methods across even large ensembles also could be or is a very, very valuable exercise, I think, because in large ensembles or kind of exercises of that sort, we actually have a true benchmark where we can test how the different methods perform, or what we should expect, even if it's kind of conceptually different methods like conditional dynamical adjustment, kind of attribution and unconditional attribution. At least we can then develop kind of an understanding of what we should expect in terms of differences in kind of a perfect model setting. And the second comment I wanted to make is that last year was in the IXAIDA European project, we made a study on what could be kind of a very cold winter in Central Europe still, even with climate change. And in that context, we also compared a couple of different methods, the conventional statistical method, Claire was also involved, and also basically dynamical adjustment methods and so on. And we were actually a bit surprised to see that they were actually in relatively good agreement. Maybe this was a relatively special, maybe it was kind of a special case, but at least in that case, there was kind of pretty good agreement between the methods. And so maybe there could be some, I mean, speaking to Claire and Davide here, but maybe there could be some interest or some good results in if, world weather attribution and ClimaMeter would kind of team up for some studies and actually compare the findings.
I don't know if I can directly reply to this. Clara, but please go on. Yeah.
No, go for it.
No, I mean, yes, we are doing this already. So we have an effort from the University of Oxford, actually, a colleague of Nick, Shirin, who is trying to compare different approach, the WWA, the ClimaMeter, and the forecast-based approach. And I think this is important. And my answer to the questions was PhD students, basically. That's, I mean, to do well the things that we are aiming to do, we need studies, in-depth studies, and only PhD theses that are like long span studies that can go into the details, or peer-reviewed studies, but like well thought. And I think that this is really something that is more research, and these research that are like long span research then gives strength to the rapid attribution frameworks that are the WWA and then ClimaMeter and many others. So I think that this kind of long-term research is what is needed to go towards.
Yeah, that's pretty much what I was about to say, that we've got a colleague of mine is working with a colleague of Davide's to do this very thing. I don't know if I would say that this is towards standardizing methods again, but it's that thing of combining different lines of evidence. I don't know if it will be possible to standardize them so that you're using the same counterfactual or an equivalent counterfactual, but I think it is really important. And I think this is kind of the way forwards, is this approach of using multiple methods. So the more methods we can make rapidly deployable, the more lines of evidence we can bring together in rapid studies and bring to the public attention. And actually, as Kate says, we have found that reporting several different lines of evidence or several related lines of evidence in a single study is not a problem for the media to understand, for the public to understand. We don't get pushback on doing that. Yeah, and as I said earlier, when we've had studies on the same, different groups doing studies on the same event, even if the results are not necessarily the same number, they're generally pointing in the same direction. And I think all that does is bolster confidence, as Peter says, rather than cause confusion.
If I can quickly jump, yeah, echoing what both Davide and Claire have said, I think it's very difficult at the moment to compare quantitative estimates, but we've got to make a start in comparing kind of qualitative. And at the end of the day, that's what people generally take from these studies is kind of, as Claire says, the lines of evidence. And the other point I would kind of hoping to make was, I feel like the impacts are somewhere where you can try and kind of bring everything back together. It depends on what, like, obviously it depends on the stakeholder, but say if you're interested in insured losses, then there are a million ways to define what a storm is in meteorological terms, but there's one way to define what the total loss is. And so that's one way in which different approaches, if you get down to the impact scale, which is very difficult, I give you that, like, are some way you can kind of bring it back to actually what the focus should be. And I don't know if it really matters whether the kind of steps before have to be perfectly standardized, but that's ultimately at the end of the day kind of what we care about. And one way we could make the results more consistent is through the impact.
Laurent, do you have any quick thoughts to add, or?
Well, no, I agree that combining methods and combining lines of evidence is of course a very nice thing to do. That's what IPCC tries to do when the assessment is done. So, but still, understanding why methods give different results in detection, in standard detection and attribution, I mean, the methods are different, but the data is usually the same. I mean, so in this case here, it's a bit more different because some of the data are not the same, the tools are not the same, so it's more complicated than to, of course, compare the methods. And then maybe the true question is whether it is truly necessary to do so, or do we have to live with the fact that, okay, they give different answers, sometimes not very different, sometimes maybe more, especially if you talk about precipitation or any sort of hydrological related events. Well, of course, for temperature, we all agree. For other types of event, I'm not so sure. But yeah, no, I agree. So, and I agree, standardized methods and not the way to go. The diversity is very good, but understand the diversity is also very good. So, and to me, so far, it's lacking.
Yeah. Well, thank you all for sharing those thoughts. It seems like the kind of quick summary of all of this is that we should continue to compare methods, perhaps find ways to compare them for similar events. And that's a useful exercise for us to do as a community, but standardizing methods, we're not at that point yet. And that's not something we should be aiming to do. Having more evidence for a particular topic is useful. So, and it's also amazing to see how much, the methodologies have advanced since the last time this report was written, and they're, as we heard from panel 2, are going to continue to have those advances. So we should aim to do more intercomparisons of methods. And Peter, you brought up a pretty challenging topic. How do we go, what do we do when science is updated and we get additional information? So this kind of brings us to this question, the topic of communication of these results. So perhaps the first question I have is around, what has your experience been with communicating your approach to the public or to different stakeholders? Yeah, what are some... Yeah, okay, let's start with that question. Is what has your experience been? Are there any particular challenges that you might have experienced in communicating your findings? So would anyone like to volunteer to start?
Can I jump in? Because I feel like it sort of addresses one of the questions in the Slido as well. So obviously most of our communication of our results is going to the media. The media loves a number. So we will work really closely with the local experts to try to get all the nuance in about the uncertainties that we found and all of the caveats and to try and really really capture that in our press briefings and when we talk to journalists. And often the stories that they write, most of the journalists, tend to reflect that quite well, actually. I think most climate reporting is pretty balanced and is able to deal with that. But the headlines that you get, as someone has flagged up, we have no control over that. And quite often the journalists have no control over that as well. That comes from an editor, I think. And we can't control what is the headline that gets put out there and that then sticks in people's heads. So all we can do is be as careful as we can with how we communicate it and to work with the media to try and educate them about how to communicate that uncertainty. Peter, Davide, I'm guessing you've got quite a lot of experience in the same sort of area. I won't go into the second part of that question in detail about the statistical significance, because I feel like there's a sort of a broader topic to talk about here. But I think requiring statistical significance always in an attribution study would mean we could never say, or we often couldn't say very much because some of these indices are so uncertain. So we try to communicate the uncertainties would be my kind of short answer to that. But we can go back to that if you want to, but I would rather let others speak first.
Yes, perhaps if I can go for ClimaMeter, first of all, it was an adventure to see how random, not random, but how different can get the communication around an event depending on many things that we don't control. One is what is happening in the world. At the same time, we do the report. If there are news that are like more pressing in the media, then this goes through much in an easier way than the attribution report. Some other times the news, there is some agency that pick up our report and then it's in all the media at the same time. And then we start to see distortions in the message that we communicate. And this is sort of error propagation. So I think we can get almost everything. And I think this is something that for the scientific community is not clear. It was not clear for me before starting ClimaMeter. And I was saying like why, for example, some report of the WWA is communicated this way. And now I totally understand it is out of control. So it's very important. And I think WWA and ClimaMeter, we both have in our website guidelines for the journalists that details on the methodology. We spend a lot of time, also time on our private life to say to the journalists how to communicate results, and this would build knowledge around our methodologies, and sometimes still out of control. And about the statistical significance in ClimaMeter, we are very conservative also because we are new. So if we don't have statistical significance, we put big title that is low confidence, prevent from attributing blah blah blah, and then we say nothing. So this may evolve in time, but because we are young, we prefer to be conservative on this side. And that's basically what I wanted to say to complete Claire.
If I could just chip in with another couple of thoughts. I think one aspect is I think we found is the context is really important. So, scientists, we're super obsessed, rightly, with the small details of what we've done. It's super important, I think, to give the big picture context. Climate is changing. There's no doubt about that. And that's really important to say that up front, right? And then to relate that big picture to the very specifics of what we've looked at, where we for example may be talking about the natural variability of the storm track over the Atlantic and nuances about how we're modeling it, etc. Another point I want to make was transparency. All of those details will be there for somebody to look at should they wish it, and we should be aware of that, and therefore have the capability to explain some of those details and journalists may well dig down into some of those super detailed stuff. And then a third point, and then is yes, the media like a number, and that can be a problem because they like one number in my experience, or they are apt to choose one number. So I think it's better that we, the scientific team, with our communication experts working with us, choose that number carefully, rather than the journalists, if we can, to Davide's point. But I take the point that that some of this is going to be beyond our control. But the more we can control the message, of course, the better.
Kate, there's actually a specific question for you and maybe anyone else that would like to comment on this about some examples of exemplary communication efforts around uncertainty to the public, to the media. If you could share some insights about that.
I mean, I think World Weather Attribution does a great job. I think, as what Peter was saying was really important, right? To say there is no weather now that is occurring not against the backdrop of a changing climate, right? And I think it can be really useful to say, here are the things that we know, right? Like nobody scientific, nobody serious is saying carbon dioxide is not a greenhouse gas. Nobody's saying it's not warming. And we know what warming means, right? Like we know what happens to the saturation vapor pressure. We know what happens to evaporation. There are things that we don't know, right? But I guess this is really, I want to turn this around. This is really more of a question than a comment. And something that I have really struggled with is bridging the scale that Peter was talking about. And then Sebastian mentioned, kind of these differences between trend attribution and event attribution. And in a lot of cases, there seems to be kind of either conflicting stories or stories that maybe if you're arguing in bad faith might seem conflicting, right? So if you look at those hexagon plots from the IPCC, there's not a lot of like 3 dots in those hexagons. There's not a lot of, we have a really robust attribution of these long-term trends to human activities. And that might seem to fly in the face of, okay, well, this heat wave is X% more likely or more severe or whatever due to human activities. And that's something that I have really struggled to bridge when I'm talking to the public. And, obviously we are operating in an environment where not everybody is acting in good faith. We are operating in an environment where there are folks who are willing to say with great confidence, there is no human influence on these events, or say something that's true, right? Like, look, the number of deaths in disasters has been declining. Therefore, this is not a problem. And I guess I kind of want to turn this back to the panel and say, this is a challenge that I have encountered, and I don't know what the right answer is. I don't know necessarily how to do this.
Yeah, would any of the panelists be able to speak about perhaps engagement with other stakeholders, like beyond communicating these findings to the media so that people can obviously contextualize what they're experiencing, but perhaps stakeholders that might use this information in some kind of decision making, and how these uncertainties are communicated to them. Like when we're talking about communicating to the media, there's certainly a lot of different actors we interact with, but a lot of stakeholders are now that recognize the importance of climate change and changes in extreme events and want to incorporate that information. So does anyone have experience perhaps with how they communicate these uncertainties in those settings? Could anyone speak to that?
I can say that we had the interaction with the French government. I don't know if this is the answer you're looking for, but for the floods in 2023, we interacted directly with the cabinet of the Prime Minister. They were interested in building a report for the population and also for the stakeholders that was showing the effect of climate change. And this was to build awareness in the stakeholders at the political level, which means the mayors of the city, the actor of the department concerned by the floods, and also the region north of France. And yeah, I mean, this was an interaction that is, what I can say is that this interaction is at the different time scale from the scale of the media. Normally it's a slow interaction, and I don't know how effective it is, because at the end, what happens is that we do this report, and by the time the report is ready, the government typically change, the political flags of the government change. So it's something that stays, and I think if it reaches the level of the territories, if it reaches the regions, the department, for you guys in US, the state level or the county level, that's what it matters to then motivate some action at the stakeholders level that really have the power to engage with that community and with the decisions.
I could introduce a couple of additional thoughts. Perhaps it was in my experience talking with people interested in adaptation in a variety of contexts. My experience, at any rate, is that the attribution question per se may not be of that great an interest, but what is of interest is current risk, the risks they care about, and current risks and how they map onto past and future risks, where it seems to me attribution does have a, the way we're thinking is relevant, but the attribution question of the counterfactual may not be of as much interest. And then another group of stakeholders, which I have only a small experience with, but which I think is very interesting, is on the legal litigation side of things. It strikes me there's a different timescale of the, these cases may last for a number of years, and therefore it's not a question of rapid attribution, but it is a question probably of very robust, stress-tested attribution, right? So I think that's an interesting forum, if you like. Because there are people in cases who will be trying to demolish, it relates to a case point about bad faith actors. I mean, it's in an oppositional sense. There's an attempt to stress test things, and I think that's an interesting avenue, and a potentially more and more important one. And we think about loss and damage, of course, the whole international loss and damage context.
Absolutely. So thank you for those thoughts. It seems like, yeah, the legal arena is where attribution science is increasingly being used, and it does create some challenges. Perhaps there, some of the standardization or intercomparison of methods that we talked about, and thinking about ways that we can, across the attribution community, think about how to communicate the findings of attribution science could benefit, at least in that particular application. So we're at 10:45. Sorry, I'm trying to convert time zones here. We have 15 minutes left, and I'd like to take a few minutes to talk about the future of extreme event attribution. And so we, as a committee, have a couple of questions for you, and perhaps I'll share one reflection I had from hearing about the from the first and second panel, thinking about like the challenges with existing attribution approaches or within attribution science, which to one extent, one of them being that we have we need good data, and we need models that reliably simulate at least the distribution of whatever variable and processes that influence these events. That is a particular challenge in parts of the world where there are highly vulnerable communities that experience large, substantial climate risks, where there's also limited amount of data. And our global climate models can also be notoriously bad in simulating some of the processes that are important in shaping climate there. So I guess with that in mind, what do you think? How do you think we can provide attribution information in places where that are data sparse, where some of this information on attribution is really important, and with the 2021 heat wave in the Pacific Northwest, we have numerous studies about one particular event, but for events that happen in parts of the global South, for example, we have maybe one, and then we throw our hands up and say, well, we don't have good data in some of these regions. But can you all maybe share some thoughts on how you think we should address our ability to provide attribution information in those data sparse areas? Kate kind of touched on that with some of her methods, but I'd be curious to hear from some of the other panelists here. Would anyone like to volunteer? Laura?
Maybe I can say a few things. Well, I mean, there's a revolution in weather forecast right now with AI methods. I mean, the Open Center, the GraphTop paper about how you would directly forecast based on observations, no model, etc. You have sparse observations, different kind of observations, and you, well, the paper is, of course, it's the first paper. It's interesting results. So certainly one way to explore, right? And then one result from the paper is that even in data where in region where you have no data, you actually get a pretty good forecast. So because you, of course, you have covariances, you have between the different variables you're using. So that's only one way I think that is very promising for the future. There's a lot of work to be done, of course, but I think it's an interesting avenue.
I can add for ClimaMeter, what we are trying to do now is we want to realize some target studies that will be peer reviewed with the analogs observation methodology. For example, for Africa, we want to attribute the 30 most impactful events in the last 5 years, and this will be something like to help to cover what is missing now in also in the hexagon plots in the IPCC. But I think, again, we are thinking how to do it well for the reason that Claire has explained in the first panel, that somehow the data sometimes are not good for some regions, so we have to acknowledge this. And in fact, we will proceed like the WWA in their study, so we will ask local scientists to help us and to contribute to this. And this will be our effort for this, and perhaps if the experiment is successful, we will repeat it for other areas that are not covered. So this will go both on the ClimaMeter website, but will be peer reviewed.
Yeah, and I think multiple panelists, I think Sebastian, you as well as, yeah, I'm trying to remember who else talked about this topic of aerosols being really important as well in some of these regions, and also limiting our ability because of how poorly some of the like aerosol processes are represented. So could you also share some thoughts on how you think perhaps attribution science should be advanced to address some of those issues?
Yeah, sure. So because you mentioned the aerosols, I mean, in the study that I presented briefly in my flash talk, we are of course not only looking at Europe and North America, because these are the two regions where we had this kind of strong negative aerosol forcing peak in the 70s and 80s. But then of course there are other regions, Southeast Asia, East Asia, and so on, where aerosols are kind of have a very different kind of developmental, like a very different kind of pattern of development over time. And so we have been, I mean, so we have been kind of trying to compare a little bit if we apply the kind of the standard world weather attribution kind of conventional statistical model, in which kind of direction the error goes, depending on how the aerosols are developing. And it's maybe interesting because the error kind of goes in the opposite direction too. So Europe and North America, you make a certain error if you ignore the aerosols with the GMST covariate, and you basically make the opposite error if you're in an area where the aerosols kind of are still increasing. And so so maybe it could be kind of these kinds of studies, I think, and world weather attribution is doing that, of course, is to kind of and ClimaMeter also, as Davide explained, to involve kind of local scientists and a lot of kind of regional and local knowledge about kind of the additional drivers of climate change beyond only greenhouse gases that are, of course, as we all know, well mixed and so on, but of course with more regional drivers like aerosols or land use may be another case that may be very different. And of course that's an area where I think both, again, kind of large ensemble simulations where we have hopefully a pretty kind of decent representation of the different regional forcings, but also kind of local and regional scientists and knowledge are, in my opinion, very important there.
And can I just follow up just to say that this point about local knowledge, local expertise, scientific expertise in countries, and the support of that, and the that's a big geopolitical question, of course, ultimately, but the collaboration and the support is really important. And you know, Red Cross, Red Crescent is a hugely important collaborator with WWA. We have a big project in Southern America, for example. These sorts of efforts, I think, are really valuable if they can be funded and supported.
Yeah, and I really appreciate the work that World Weather Attribution does in connecting with many of the local stakeholders and scientists. Nick, would you have any thoughts to share, since you had briefly in your talk mentioned something about being able to attribute events, or at least doing some work towards attributing events that occur at subgrid scales, or like finer scales that we aren't able to simulate well with our models. So could you briefly talk about that as well?
Yeah, I mean, I think, yeah, it's just going to sound biased based on where I'm coming from, but like leveraging advances in weather forecasting, that like the ones that Laurent has just mentioned, kind of that like make use of the tools that we've got, the best tools that we've got, that we know, like that we trust to forecast the weather on a day-to-day basis. Like, let's make more use of those to answer the kinds of climate questions, not just using those kind of solely, but like in the kind of toolbox that we have sort of assembled with this panel, then let's make the best use of those. And yeah, like the example earlier was just a kind of throwaway one, but like there is a lot of research that and studies that are written about how, like, kind of building on top of weather forecasts that potentially could be very useful for extreme weather attribution. We just need the kind of, I guess, approaches that can make use of that.
And can I just say that coming from an institution that does weather forecasting, I find this forecast attribution really exciting scientifically and also really powerful communication tool. So I can really see the potential of this.
Absolutely. We look forward to seeing what else comes out of this group. So we have 3 minutes left. And before I turn it over to Jim, I wanted to ask one quick question. Hopefully I'll give 30 seconds to everybody to answer. What do you think are some of the highest priorities in attribution science? Maybe share one highest priority in attribution science to meet the needs of adaptation planning or local decision-making or informing loss and damage funds. The process for that. And I'll start with Claire.
Oh, I was really hoping you weren't going to say that. I think I am going to reiterate what we've just been saying quite a lot, actually, is that building capacity with the local scientists and getting their perspectives on what they need to be able to attribute in their regions is really important, because we can sit here and say, I think you need this, and that might not be what you need in that area. I don't know. I'm not an expert in South American climate, African climate. I do attribution generally. And so I think maybe that's the approach that we need to take, is kind of bringing together other people's expertise and training people up to let them figure out what they need. Yeah.
Kate?
This is not just me. Our center director wrote an op-ed about it in the New York Times recently, but I think it would be really useful to think about how we make the GCMs, the sort of CMIP GCMs, much more responsive and able to answer questions like, for example, why was 2023 so hot? Why was 2024 so hot? And I think there's a lot of opportunity to kind of bridge the scales. It obviously wouldn't be rapid event attribution, but it would be doing something a little bit more rapid with the GCMs that doesn't entail waiting a long time for forcing data to come online and doing the runs over a really, really extended sort of CMIP timescale.
Laurent?
Hoping to see more combined studies based on different methods, different kinds of evidence, addressing the hard challenges. For example, in complex orographic regions, even kilometer scale models have huge temperature biases over mountains. So if you are looking at an extreme event over a mountain, even with kilometer scale models, you'll still have a lot of problems. And of course, you have the observation problems. So there are efforts in different parts of the world to try to build up some new observed data sets, combining all the data you can get. And that's very, very, very important, especially in these regions where the challenges are very high, since they're very local, small scale effects, very complex physics, and that even our best forecast models are not able to completely overcome these problems. So a hard challenge for the future.
Thanks. Sebastian?
This is maybe not the most important, but one thing that I think could be very interesting and good, also for adaptation planning and risk estimation, is that attribution so far looks into kind of almost entirely events that have happened, but I think it could be very useful to look also into events that have not happened, but may happen. So questions like, what if something analogous to the Canadian heat wave from 2021 would happen somewhere else in the world and where we just happen to not have seen it? I think that's an area where attribution could contribute very productively to inform adaptation and risk assessments.
Jim, do we have time to make it through the panel, or should we wrap up?
Let's wrap up in 1 minute.
Okay. Okay. So we have 1 minute and three more people. So you have 20 seconds each. Davide?
Yes, I wish that we go towards damage attribution, impacts attribution, and I also wish that we stay together and united as a community of scientists, because this is a challenge that we go towards the entire world, and we have a scientific and also human responsibility when we do attribution.
Nick?
It's an ever decreasing number of answers to this, but I'm going to agree with Sebastian and Davide in particular, like reframing from a backward-looking problem to a forward-looking one with an emphasis on kind of physical process understanding.
Mm-hmm.
Yeah, is that the last to me? So yeah, I agree with that. Stick together,
Yeah.
and let's bring in the social scientists and the decision makers into this whole thing. Let's conceptually get into a room and work the problem together.
Thanks, everyone. Thank you all for your fabulous talks, for the really productive discussions, and for sharing your perspectives on the future of attribution science. And I'll pass it over to Jim.
All right, I will close this out very quickly. I would also just like to once again thank all 7 of our speakers and panelists today. I learned a tremendous amount, a lot of things to think further about. This has been extremely informative for the committee's deliberations and ultimately our writing of the report. So thank you all very much. We've taken up 3 hours of your time. That's a big chunk of time for very, very busy people. Unfortunately, I'll say you're not 100% off the hook, because there may be some additional follow-up questions or things we didn't get to today that we will reach out and ask you about in writing. So thank you very much. Also like to thank the moderators, Kevin, Danielle, and Dipti, for doing a great job moderating these sessions. Just a reminder for anyone who's still online, on March 11th, we have another information gathering session. It's going to be on process-based modeling approaches for attribution science. Then in April in Irvine, California, we're going to have a hybrid workshop focused on impact attribution, which is a topic that came up a bit today, and we'll explore that further in April. So thanks to all of you, thanks to the full committee, and also thanks to any members of the community and the public who joined us online. We have captured your questions. This will entirely be posted, will be posted in its entirety on the committee webpage. So keep an eye out for that. Thank you all very much. And with that, we'll close this session. Really appreciate it.